Is emptiness truly empty, or the hidden engine of creation? How do quantum fields turn nothing into the structure of everything? Can the restless vacuum help us understand both the cosmos and ourselves? Even as we end one chapter, the idea of nothing continues to invite reflection. Throughout history, thinkers have used emptiness as a metaphor for potential. In mathematics, the empty set is the foundation on which all numbers are built. From nothing comes the structure of counting. In art, blank canvas and silence are used intentionally, letting the viewer or listener fill the space with emotion. These analogies remind us that nothingness often acts as a fertile ground. It is not a sterile absence, but a pause, a space where possibilities can take shape. This insight resonates with the physics of the vacuum. Emptiness is a canvas for fields to play, an interval that invites creation. Language itself hints at our unease with nothing. We speak of voids and vacancies, yet these words carry more than pure absence. A void suggests something missing that could be filled. A vacancy implies a place where someone could stay. Even the word nothing is a linguistic construction, a thing we talk about. Perhaps this suggests that our minds cannot truly conceive of absolute non-existence. Instead, we intuitively overlay potential and expectation onto emptiness. In doing so, we mirror the physical understanding that a vacuum is not empty, but holds the seeds of future events. Our language betrays our deep connection to the world's structure. Another way to appreciate fields is to think of them as the essential substance of the universe. In everyday life, we talk about matter and energy. In quantum field theory, matter is built from fields. The electron field gives rise to electrons, the quark fields to protons and neutrons. The photon field mediates electromagnetic forces. These fields interact with each other, sometimes merging temporarily into composite excitations, sometimes annihilating each other. The richness of the particle zoo emerges from the interplay of a few fundamental fields. This perspective replaces the notion of particles moving through empty space with a vision of the universe as a system of overlapping, dynamic fields. When we zoom in on a small volume of space, we can imagine the electron field there fluctuating. In one moment, the field value might be slightly higher. In the next, slightly lower. These changes are random within constraints set by the uncertainty principle. If a photon passes by, it might interact with the electron field, creating a real electron-positron pair if enough energy is available. Otherwise, it causes a virtual fluctuation that quickly disappears. The distinction between real and virtual is thus not fundamental to the field itself. It depends on whether energy is supplied externally to sustain the excitation. The vacuum holds within it the potential for both. The Heisenberg uncertainty principle has far-reaching consequences beyond the simple statement about position and momentum. In the frequency domain, it manifests as an uncertainty between the energy of a system and the time interval over which we define that energy. A short-lived process can borrow a large amount of energy as long as it pays it back quickly. This time-energy uncertainty is less often quoted in textbooks because time is not an operator in quantum mechanics. Yet it is vital for understanding the fleeting nature of virtual states. The interplay of time and energy defines the window during which a quantum fluctuation can manifest, before it must merge back into the sea of possibilities. Measurements of tiny systems reveal the limits of our knowledge and control. In laser-cooled atomic traps, physicists use photons to hold and manipulate atoms, yet each photon imparts a recoil. Lowering the temperature of the atoms increases their localization, but also raises their momentum uncertainty. A similar trade-off appears in the design of gravitational wave detectors, where measuring distances to extraordinary precision introduces quantum back-action. To push beyond the standard quantum limit, engineers use squeezed light, altering the uncertainty distribution between variables. These experimental endeavors embody the uncertainty principle, turning it from an abstract statement into a practical engineering constraint. In our journey through zero-point energy, it is worth noting that this vacuum vibration can influence chemistry. In molecules, the zero-point energy of vibrational modes raises the baseline energy and affects reaction rates. Isotopes with heavier nuclei vibrate more slowly, leading to slightly different zero-point energies and thus different chemical behavior. This isotope effect plays a crucial role in biochemistry and atmospheric science. Without zero-point energy, the differences would vanish. Thus, quantum vibrations shape not only cosmic expansion, but also the taste of wine and the mechanisms of life. The vacuum's whisper resonates in surprising corners of reality. The idea that zero-point energy might be harnessed as a source of free energy has long fascinated inventors and conspiracy theorists. They imagine devices that tap into the vacuum's endless reservoir, delivering power without fuel. Physicists respond that while the vacuum energy is real, extracting network from it is forbidden by thermodynamic principles. Energy differences can be harnessed, as in the Casimir effect, but the uniform, pervasive background cannot. Any attempt to extract energy would require creating a lower energy vacuum state, and the energy required to do so would exceed the energy gained. The vacuum is restless, but not a perpetual motion machine. The Casimir effect also teaches us about geometry's influence on quantum fields. Between parallel plates, only certain wavelengths fit. Between a plate and a sphere, or inside a cylindrical cavity, the allowed modes differ. As a result, Casimir forces can be repulsive as well as attractive, depending on the shape and materials. Researchers have observed repulsive Casimir forces in carefully designed setups using metamaterials and exotic configurations. These experiments confirm the flexibility of the vacuum's response. They also inspire designs for nanoscale machines, where Casimir forces act as springs or dampers. Understanding how the vacuum responds to geometry opens new avenues for engineering at the smallest scales. Within the language of Feynman diagrams, virtual particles appear in loops that correct the simple tree-level interactions. These loops represent the contribution of all possible intermediate states the system can explore. At high energies, loops from heavy particles become important, affecting the running of couplings. At low energies, most virtual contributions decouple. This energy dependence explains why the vacuum appears different when probed at different scales. It is as if the vacuum holds a layered structure, with certain features becoming visible only when we focus our attention finely enough. These layers echo the concept of renormalization, which systematically accounts for how physics changes with scale. There is also an interplay between virtual particles and real thermal excitations. At finite temperature, fields do not sit in their ground state, but are populated with thermal quanta. This thermal bath modifies the vacuum fluctuations, altering the Casimir force and the vacuum's energy density. In cosmology, the early universe's high temperature meant that the vacuum and thermal contributions were intertwined. As the universe cooled, phase transitions occurred, changing the vacuum structure. The quark-gluon plasma condensed into hadrons, and later the electroweak symmetry broke, giving mass to particles through the Higgs field. These changes in the vacuum's configuration underscore its dynamic, evolving nature. The measurement problem touches not only physics, but also questions of consciousness and information. Some interpretations of quantum mechanics, such as the relational interpretation, suggest that properties are defined only relative to observers. Others, like cubism, view quantum states as expressions of personal belief about measurement outcomes. These perspectives highlight that measurement is not just a physical act, but a cognitive one, involving knowledge and belief. Our understanding of the vacuum is thus intertwined with epistemology. What can we know, and how do we justify our beliefs about unseen processes? Exploring these questions adds depth to our study of nothingness. Every measurement produces data, and data must be stored. Atoms in a memory device must switch states to record a bit. This switching dissipates heat and requires energy, connecting computation to thermodynamics. Landauer's principle quantifies the minimal energy cost of erasing a bit of information. The interplay between information and physical resources means that understanding the vacuum's fluctuations may also inform the limits of computing and communication. Quantum information theory uses entanglement, itself a property of the vacuum, as a resource. Quantum bits, qubits, can be in superpositions, enabling new forms of computation. However, decoherence threatens these fragile states. Protecting qubits from environmental noise is a modern challenge that sits at the intersection of nothingness and technology. Decoherence has been observed in many experiments. In a classic demonstration, atoms are sent through a double slit, creating an interference pattern. If a light beam is used to detect through which slit an atom passes, the interference pattern fades. The interaction with light correlates the atom's path with the environment, causing decoherence. In superconducting qubits, coupling to stray magnetic fields or phonons causes decoherence, limiting the coherence time. By engineering the environment, scientists have extended coherence times, showing that decoherence is not inevitable, but depends on the interplay between system and environment. These experiments provide practical insights into the boundary between quantum and classical. The debate about whether decoherence solves the measurement problem continues. Some argue that decoherence explains why we never observe superpositions of macroscopic states like alive and dead cats. Others point out that decoherence gives probabilities but not outcomes. Newer approaches, such as objective collapse theories, propose modifications to quantum mechanics that introduce spontaneous collapses. These collapses would occur more readily for larger systems, explaining why macroscopic superpositions are not observed. While objective collapse has yet to be verified, the search for a deeper understanding of measurement drives theoretical and experimental innovation. Whatever the outcome, the interplay between decoherence and reality remains central to our exploration of the quantum vacuum. When we consider the universe as a whole, decoherence takes on a cosmic scale. The cosmic microwave background, CMB, is a fossil record of the universe about 380,000 years after the Big Bang. Tiny temperature variations in the CMB correspond to density fluctuations. These fluctuations are believed to have originated from quantum fluctuations during inflation that decohered as they were stretched across the cosmos. The environment in this case is the rest of the universe, with which each region becomes entangled. The patterns imprinted on the sky are thus records of quantum events writ large. This profound connection between microphysics and cosmology illustrates the unifying power of decoherence. Dark energy, whether a cosmological constant or a dynamic field, also interacts subtly with the vacuum. If dark energy is a field, it could fluctuate and evolve, perhaps interacting with other fields. Such quintessence models predict that the dark energy density changes over time, affecting cosmic acceleration. Observations constrain these models, but have not ruled them out. In any case, the existence of dark energy implies that the vacuum's properties can influence the universe's fate on the largest scales. The vacuum is not just a backdrop, it is an active component of cosmic evolution. Cosmic expansion also affects how we perceive nothingness. In an accelerating universe, horizons arise. There are regions of space that can never influence each other because the expansion is too rapid. These horizons limit what observers can see and measure. In such a universe, each observer's accessible portion of the cosmos shrinks over time. The vacuum energy that drives acceleration thus also governs the information we can access. In the distant future, observers in isolated galaxies may see only their own island of stars, unaware of the broader universe. The vacuum sets the stage not only for physics, but for our cosmic perspective. Some physicists hope that a theory of quantum gravity will illuminate the cosmological constant problem. String theory, for example, offers a landscape of possible vacuum states with different energy densities. In this picture, our universe resides in one of many possible minima, with a small but non-zero vacuum energy. The anthropic principle suggests that only universes with small cosmological constants can harbour structures and observers, offering a possible selection mechanism. Loop quantum gravity and other approaches propose discrete spacetime structures that might change how vacuum energy interacts with gravity. These theoretical endeavours are driven by the profound mismatch between quantum field theory's predictions and cosmology's observations. At smaller scales, experimental tests of gravity and the vacuum probe the interplay between the quantum and gravitational realms. Precision measurements of the gravitational constant, experiments with ultra-cold neutrons in gravitational potential wells, and attempts to detect gravitational Casimir-like effects explore territory where quantum mechanics and general relativity overlap. Although a fully quantum theory of gravity remains elusive, these experiments constrain theories and hint at how spacetime might behave at tiny scales. They remind us that the vacuum is not only full of fields, but is itself shaped by the geometry of spacetime. The idea of scales also invites us to compare the vacuum in different environments. Inside a solid, electrons fill energy bands, and the electromagnetic field interacts strongly with matter. The local vacuum in such a medium differs from the vacuum in free space. Photons acquire effective masses and slow down. Virtual processes are screened. In the core of a neutron star, where densities are immense, the vacuum may undergo phase transitions, possibly creating exotic states like quark matter or color superconductors. Studying these extreme environments extends our understanding of what emptiness can be, revealing that the vacuum is context-dependent. In technology, controlling the vacuum is essential. Electron microscopes operate in high vacuum to avoid scattering electrons. Particle accelerators require ultra-high vacuum for beams to travel unobstructed. Vacuum chambers allow researchers to cool atoms to near absolute zero, study exotic states of matter, and test fundamental laws. These practical vacua are not perfect. Stray molecules and electromagnetic fields remain. Engineers therefore push the boundaries of vacuum technology, combining materials, pumps, and traps to create ever better approximations of emptiness. Each improvement reveals new subtleties in how fields behave when freed from external clutter. The interplay between nothingness and creativity is also evident in the arts. Composers use rests and silence to create tension and release. Painters use negative space to draw attention to the subject. Writers use white space and pauses to evoke mood. These artistic uses of emptiness echo the physical insight that absence can be as significant as presence. In both art and physics, empty regions are not ignored. They are actively shaped to influence the outcome. Understanding the vacuum thus inspires a broader appreciation of the role of space, silence, and absence in human expression. In daily life, the vacuum plays subtle roles. The pressure of the atmosphere above us is balanced by internal pressures in our bodies. When we drink through a straw, we create a partial vacuum that allows atmospheric pressure to push the liquid up. Vacuum cleaners work by creating low-pressure regions that air rushes into, carrying dust. On a grander scale, vacuums are used in manufacturing to deposit thin films, create integrated circuits, and test space-bound equipment. Even though these vacua are not absolute, they are good enough to illustrate how removing air changes the behavior of systems. These examples remind us that controlling emptiness is a powerful tool. Historically, the idea of vacuum faced resistance. Aristotle believed that nature abhors a vacuum and that any void would be instantly filled. This view persisted for centuries, influencing physics and philosophy. Experiments in the 17th century, such as Torricelli's barometer, demonstrated that a column of mercury could be supported by atmospheric pressure, leaving a space at the top with very low density. This space was not truly empty, but it challenged the notion that vacua were impossible. Gradually, scientists accepted that space could be largely devoid of matter, while still being filled with something, though the understanding of fields came much later. The evolution of the vacuum concept mirrors the broader scientific journey from intuition to experiment to theory. The birth of quantum field theory in the 20th century transformed our understanding of the vacuum. The quantization of the electromagnetic field led to the concept of photons, while Dirac's theory of electrons predicted antiparticles. The discovery of the Dirac sea suggested that the vacuum is a filled state of negative energy electron states. Later, this picture was refined to a more abstract view of fields with creation and annihilation operators. Each step stripped away classical analogies and replaced them with more accurate but less intuitive descriptions. Yet the thread running through these developments is the recognition that emptiness is not simple. The vacuum is structured, active, and central to physics. Manipulating vacuum energy differences is an active area of research. In superconducting circuits, artificial atoms couple to transmission lines, creating resonant cavities. By changing boundary conditions on ultra-fast timescales, researchers can create photons out of the vacuum. This dynamic Casimir effect has been observed experimentally, providing another example of how the vacuum responds to changing conditions. In analog gravity experiments, scientists simulate event horizons in fluids, or Bose-Einstein condensates, and observe phenomena akin to Hawking radiation, where pair creation at horizons leads to radiation. These analog systems offer glimpses into how vacuum fluctuations manifest in extreme environments, bridging quantum field theory and gravity. The role of symmetry in determining vacuum states cannot be overstated. Spontaneous symmetry breaking occurs when the lowest energy configuration of a system does not share the symmetry of the underlying laws. The Higgs mechanism is a prime example. The electroweak theory is symmetric, but the vacuum chooses a specific orientation of the Higgs field. This choice gives masses to W and Z bosons and leaves the photon massless. Similarly, in ferromagnets, the vacuum chooses a direction for the magnetization. The multitude of possible vacua in certain theories, such as in supersymmetry, leads to a landscape of potential universes. How the universe selects its vacuum state is a question with deep cosmological implications. Supernova observations that revealed cosmic acceleration were a surprise. Astronomers expected the universe's expansion to slow because of gravity. Instead, Type 1a supernovae appeared dimmer than expected, indicating they were farther away. This discovery won the Nobel Prize in Physics and sparked new questions. Why is the expansion accelerating? What is the nature of dark energy? These questions turned the vacuum from a curiosity into a central player in cosmology. The vacuum's properties are not just academic. They determine the destiny of galaxies and the distribution of matter. Understanding dark energy is now one of the most pressing problems in physics. Observations of the cosmic microwave background provide precise measurements of the universe's composition. Satellites like WMAP and Planck have mapped the temperature fluctuations across the sky with high accuracy. These data show that baryonic matter, dark matter, and dark energy have specific proportions. The pattern of fluctuations also constrains the curvature of space and the spectrum of primordial perturbations. By comparing these observations with theories of inflation, physicists gain insights into the physics of the early universe. The fact that quantum fluctuations can be stretched to cosmic scales and become galaxies is a remarkable testament to the power of the vacuum. On smaller scales, precision measurements of atomic energy levels, magnetic moments, and scattering cross-sections test quantum field theory. The agreement between theory and experiment to many decimal places confirms the reality of vacuum fluctuations and virtual particles. For example, the anomalous magnetic moment of the electron includes contributions from loops with virtual particles. Its measured value matches the theoretical prediction when vacuum corrections are included. Any deviation would hint at new physics. Thus, the vacuum not only influences cosmic expansion, but also shapes the properties of electrons in our everyday devices. This unity across scales is one of the wonders of modern physics. The interplay between mass and the vacuum is particularly striking. In the Standard Model, most of the mass of ordinary matter comes from the binding energy of quarks and gluons in protons and neutrons, rather than from the masses of the quarks themselves. The strong force, mediated by gluons, is so intense that it confines quarks, creating a huge energy density inside nucleons. This energy arises from the vacuum's response to color fields and accounts for nearly all the mass in the visible universe. The Higgs field gives mass to fundamental particles, but the strong interaction and the vacuum of quantum chromodynamics do most of the work in giving heft to everyday objects. We can also look to experiments in condensed matter physics for analogies to the quantum vacuum. In superfluid helium or Bose-Einstein condensates, collective excitations behave like phonons, with dispersion relations similar to those of particles in relativistic field theories. Topological defects in these systems mimic cosmic strings or domain walls. By studying these analogues, physicists gain insights into phenomena that are difficult to access directly in high-energy experiments or cosmological observations. The vacuum, in this sense, becomes a concept that transcends disciplinary boundaries, linking the physics of solids, fluids, high-energy particles, and the cosmos. The philosophical ramifications of a full vacuum are equally rich. If our existence depends on the vacuum's specific properties, then the nature of nothingness becomes a precondition for life. Contemplating this leads some to anthropic reasoning. Perhaps we find the vacuum energy to be small, because only in such universes can observers exist. Others resist this conclusion, hoping for a deeper principle that uniquely determines the vacuum. Whether or not the anthropic principle holds sway, the idea that emptiness could determine our existence invites humility. We depend on subtle cancellations and balances that we did not design. The vacuum is not only a physical state, but a determinant of history. On a personal level, reflecting on nothingness can change our relationship to the world. Recognizing that the seemingly solid ground is mostly empty space filled with fields can evoke awe. It can also serve as a metaphor for resilience. Like the vacuum, we can be calm on the surface, yet brimming with potential energy and possibility. The idea that the smallest fluctuations can grow into galaxies may inspire us to see our smallest actions as seeds of larger effects. The quantum universe suggests that the line between nothing and something is thin and permeable. Our lives, like the cosmos, emerge from subtle dances of energy and chance. As we look ahead to the continuation of this story, we can anticipate exploring how structure emerges from the vacuum. In the next part, we may delve into the processes that turn quantum fluctuations into stars, the role of gravity in shaping matter, and the evolution of complexity. We will see how the early universe cooled and how symmetries broke, leading to the diversity of particles and forces. We will consider how galaxies formed, how life arose, and how consciousness reflects on its own origins. Each thread will trace back to the restless vacuum, showing that nothing is the womb of everything. With patience and wonder, we will continue to explore how reality emerges from nothing. In many contemplative traditions, emptiness is not a lack, but a fullness. Zen teachers speak of the void as something one can enter and find peace, not dread. The practice of quieting the mind allows thoughts to arise and dissipate without attachment. This mental spaciousness can be compared with the quantum vacuum. It is always there, underlying everything, and it can give rise to phenomena when conditions are right. Understanding physical nothingness might thus enrich our spiritual vocabulary, and vice versa. Both physics and meditation suggest that what seems empty can be a source of insight and creativity. The boundary between quantum and classical, between potential and actuality, is fuzzy. In the macroscopic world, we assume that objects have definite positions and properties. Yet at the microscopic scale, superpositions and uncertainties dominate. The process by which one regime gives way to the other involves decoherence and information loss to the environment. In this way, the world of everyday experience emerges from the underlying quantum substrate. Recognizing this helps us see that classical certainty is a special, approximate description. The vacuum's restless fluctuations are the ocean beneath the calm surface of our familiar world. The mathematical roots of the uncertainty principle lie in the Fourier transform, which relates a function to its frequency components. A wave packet cannot be both sharply localized in position and in momentum space, because narrowing one domain spreads the other. This mathematical fact has physical consequences. A particle described by a wave packet has intrinsic uncertainties in its observables. When we speak of the vacuum as fluctuating, we are acknowledging that the field's wave packets cannot be infinitely narrow in all conjugate variables. Thus, the uncertainty principle is not an arbitrary rule. It is grounded in the properties of waves and their mathematical representation. In Richard Feynman's path integral formulation, the quantum amplitude for a process is obtained by summing over all possible trajectories, weighted by their action. In this picture, even a particle moving through a vacuum explores an infinity of virtual paths. The path integral emphasizes that the vacuum itself contributes to the amplitude, because vacuum fluctuations fill spacetime with possible histories. This perspective inspires a sense of abundance within emptiness. The classical path emerges as a stationary phase, approximation to an underlying sum over wildly different possibilities. The vacuum, far from being static, is the stage for a huge ensemble of unseen histories. Astronomy gives us a vivid sense of how horizons shape our knowledge. The observable universe is bounded by the cosmic light horizon. The distance light has travelled since the Big Bang. Beyond that horizon, there are regions we cannot see. Within the horizon, the accelerated expansion caused by dark energy creates a cosmic event horizon. Some galaxies already recede faster than light relative to us, their light never reaching us. These horizons show how the vacuum's energy affects the very limits of our information. Thinking about what lies beyond them invites us to imagine how our knowledge is shaped by the dynamics of nothingness. During inflation, quantum fluctuations in the inflaton field were stretched to macroscopic scales. When inflation ended, these fluctuations became imprinted as slight density variations. Over billions of years, gravity amplified these variations, leading to the cosmic web of filaments and voids that crisscross the universe. Galaxies formed in the denser regions, and stars ignited in their cores. The cosmic microwave background still carries the imprint of those primordial fluctuations. Thus, the structure of the universe can be traced back to the quantum behavior of a field in what was almost empty space. The vacuum, in its earliest whisperings, planted the seeds of everything we see. The vacuum hosts other cosmic backgrounds besides the CMB, a sea of neutrinos. The cosmic neutrino background permeates space. These relic neutrinos are remnants from the early universe, decoupling when the universe was seconds old. Though they are hard to detect, their existence follows from the same thermodynamic principles that give rise to the CMB. There is also a cosmic background of gravitational waves, ripples in spacetime produced by inflation, cosmic strings, and merging black holes. These backgrounds remind us that emptiness is filled with subtle, pervasive relics of the universe's earliest moments, continuously travelling through us. Vacuum polarization illustrates how the vacuum responds to charges. When a charged particle is placed in a vacuum, virtual pairs of particles and antiparticles appear and arrange themselves in such a way as to reduce the effective charge seen at long distances. This screening effect is a hallmark of quantum electrodynamics. The electric field is not just emanating from the particle, it is shaped by the vacuum's fluctuating charges. Conversely, in the strong force, the vacuum exhibits anti-screening. The effective interaction becomes stronger at long distances. These behaviors underscore that vacuum is not passive, but participates actively in the dynamics of forces. Emergent phenomena in condensed matter systems offer analogies to vacuum behavior. Superconductivity arises when electrons pair up and condense into a collective state that can conduct electricity without resistance. This pairing is mediated by phonons, quantized vibrations of the lattice. The superconducting state acts as a new vacuum for electron excitations, with its own spectrum of collective modes. Similarly, in superfluid helium, the fluid flows without viscosity because its ground state has a macroscopic quantum coherence. These examples show that the concept of a vacuum as a ground state with specific properties applies widely across physics, not just to empty space. The measurement process can be understood as an entanglement between a quantum system and a measuring apparatus. When a spin interacts with a detector, the combined system evolves into an entangled state in which the spin's possibilities are correlated with different states of the detector. Decoherence then spreads this correlation into the environment, making interference effects unobservable. In this view, the definitive outcome we see is not because the wave function collapsed, but because we become entangled with a particular branch. The vacuum thus plays a role in measurement. It carries away coherence and acts as the medium through which entanglement spreads. General relativity teaches us that mass and energy curve spacetime. The vacuum energy density, though extremely small, contributes to this curvature. Einstein's equations can be written as geometry equals matter, with vacuum energy acting as a uniform source. When the vacuum energy dominates, it drives accelerated expansion. Conversely, in a region devoid of matter and with negligible vacuum energy, spacetime can be flat. The interplay between geometry and energy underscores that the vacuum's properties determine the shape of the universe. Nothingness, through its energy density, can curve the cosmos, demonstrating that absence and shape are intimately linked. From the standpoint of quantum mechanics, time evolution is governed by unitary operators, meaning that information is preserved. Even when decoherence appears to erase information locally, the total system retains it. In black hole physics, this principle leads to the information paradox. What happens to information that falls into a black hole? If Hawking radiation is purely thermal, information seems to vanish, violating unitarity. Resolving this paradox may involve entanglement across horizons, subtle correlations in the radiation, or new insights into quantum gravity. Once again, the vacuum and its fluctuations are implicated in deep questions about how information behaves in the universe. The concept of entanglement entropy quantifies how much information is shared between subsystems. In a quantum field, dividing space into two regions creates entanglement across the boundary. The entanglement entropy scales with the boundary's area, a hint of the holographic principle in quantum gravity. The vacuum's entanglement structure underlies this scaling. Thinking about entanglement across horizons leads to ideas like the ER equals EPR conjecture, which posits a connection between entangled particles and wormholes. Though speculative, these ideas point to a profound link between space-time geometry, entanglement, and the vacuum state. After inflation ended, the universe underwent a reheating phase, where the inflaton's energy was converted into particles and radiation. This process filled the vacuum with a hot plasma. As it cooled, matter and radiation decoupled, and the vacuum's energy content changed. Understanding reheating requires both quantum field theory and cosmology. It shows that the vacuum state is not static, but can undergo transitions, releasing and absorbing energy. The story of the universe is a story of the vacuum-changing state, each shift opening new possibilities for structure and complexity. Neutrinos and gravitational waves provide windows into the vacuum at different scales. Neutrinos rarely interact, so they travel vast distances unimpeded, carrying information about processes deep within stars, or from the early universe. Gravitational waves distort spacetime itself, and their detection by observatories like LIGO and Virgo confirmed a century-old prediction of general relativity. These waves travel through the vacuum without losing energy to it, but their existence depends on spacetime's flexibility. That we can detect such subtle ripples speaks to our ingenuity and to the vacuum's transparency to gravitational phenomena. Anthropic reasoning remains contentious. On one hand, it may explain why we observe a small cosmological constant. Only such universes support life. On the other hand, it seems unscientific to rely on our existence as an explanatory principle. Critics argue that we should seek physical mechanisms that determine vacuum properties. Proponents counter that if there is a multiverse with many vacua, anthropic arguments become natural. Regardless of one's stance, the discussion underscores that the vacuum's properties are intimately tied to the question of why the universe is hospitable to life. Nothingness thus becomes a topic in the philosophy of science. Mathematics and physics share a deep relationship in exploring the vacuum. Concepts like Hilbert spaces, operators, and symmetries provide the language of quantum field theory. The mathematical structures seem to exist independent of our world, yet they describe the world accurately. This uncanny fit raises philosophical questions about the nature of mathematics. Is it discovered or invented? When we ask why the vacuum obeys certain symmetries or supports certain fields, we are also asking why certain mathematical structures are realized in nature. Studying nothingness therefore brings us to the border between physics and the philosophy of mathematics. The vacuum in solids can be engineered. In semiconductors, doping introduces impurities that create energy levels within the band gap. Electrons and holes in these materials behave like relativistic particles in effective vacuum states with different properties. By stacking two-dimensional materials like graphene, engineers create moire patterns that modify the electronic vacuum, leading to exotic states such as superconductivity at relatively high temperatures. These engineered vacua are testbeds for exploring how altering boundary conditions and interactions changes the ground state. They show that by shaping the vacuum, we can discover new phases of matter and perhaps learn about more fundamental vacua. Topological defects, such as cosmic strings, domain walls, and monopolies, may arise from symmetry-breaking transitions in the early universe. These defects would be regions where the vacuum state differs from its surroundings, while searches for such defects have not yet found them. Their possible existence reminds us that the vacuum can support rich structure. In condensed matter systems, analogous defects appear when systems are cooled through phase transitions. By studying vortices in superfluids or dislocations in crystals, we gain insight into what might have occurred in the early cosmos. The vacuum is not always uniform. It can be stitched together with seams marking ancient transitions. Within atoms, most of the volume is empty space. Electrons occupy orbitals that are mainly probability clouds rather than hard shells. The nucleus is tiny relative to the atom, and the electron's wave function extends far beyond. This emptiness does not make the atom fragile. The forces mediated by the vacuum, electromagnetic interactions, hold the atom together. Recognizing that matter is mostly vacuum helps us appreciate that solidity is a phenomenon emerging from the interplay of fields rather than from densely packed substance. Our own bodies are largely empty space, yet they feel firm because of the quantum vacuum's forces. Thinking about emptiness can alter our understanding of measurement. In quantum mechanics, a measurement device must interact with the system. The vacuum supports this interaction by mediating forces. Light travels through the vacuum to carry information. Without a vacuum filled with electromagnetic field, measurement as we know it would be impossible. Thus, the ability to observe arises from the vacuum's responsiveness. This perspective suggests that observation and nothingness are not opposites, but partners. We can observe because emptiness is active. The accelerating expansion of the universe affects the flow of time. In relativity, time and space are intertwined, and the expansion stretches timescales along with distances. In a dark energy-dominated universe, the Hubble parameter tends toward a constant, meaning that the expansion becomes exponential. Time itself has horizons. There are events we will never see because they occur beyond our future light cone. The vacuum energy sets the pace of cosmic time, subtly influencing our long-term future. Even our sense of time's arrow, tied to entropy increase, is connected to how the vacuum enables records and memories to persist. Fields and their excitations form a continuum between the vacuum and the world. A photon is an excitation of the electromagnetic field that can be as faint as a single quantum or as intense as a laser beam. Phonons are excitations of a lattice, rotons of a superfluid, magnons of a magnet. Each arises from a specific vacuum state with its own symmetries and excitations. By studying these diverse systems, we see that the concept of vacuum is relative. What is vacuum to one particle is a medium to another. The richness of physical phenomena stems from the different ways fields can be arranged and excited. Returning to human experience, contemplating nothing can be both unsettling and liberating. It reminds us of our fragility and the contingency of existence. Yet it also invites wonder at the depth of the universe, recognizing that the vacuum is not a dead void, but a living sea of potential, can inspire a sense of connection. We are part of a universe in which even absence is creative. This realization can cultivate humility and curiosity. The study of nothing becomes a meditation on being, inviting us to look beyond the surface and explore the underlying patterns that give rise to reality. Finally, the interplay between nothingness and infinity invites reflection. In mathematics, an infinite series may sum to a finite value. Infinite possibilities may lead to a tangible outcome. Likewise, the infinite sum of zero-point energies must be regularized to yield finite, measurable differences. Physics teaches us to be wary of infinities and to interpret them carefully. When we speak of nothing, we must remember that it is never truly devoid of content or context. The vacuum is infinite in extent, but finite in its measurable effects. Embracing this duality helps us navigate the paradoxes that arise when we push our concepts to their extremes. Having traced these myriad threads, we see that emptiness is not an absence, but a foundation. It permeates our lives and the cosmos, shaping interactions, generating phenomena, and constraining possibilities. In the next part, we will continue this exploration, looking at how structure, complexity, and meaning arise. The vacuum will remain our silent partner, a dynamic backdrop to everything that unfolds. Our journey through nothingness thus opens the door to understanding everything. The vacuum also plays a role in our understanding of dark matter. Unlike dark energy, dark matter does not drive cosmic acceleration. It exerts gravitational pull that binds galaxies. It is invisible because it does not interact with light, but it may interact with ordinary matter through weak or other unknown forces. If dark matter particles exist, they are excitations of a field that permeates the vacuum. Searches for dark matter in underground detectors and colliders probe the vacuum for rare interactions. Whether dark matter is made of weakly interacting massive particles, axions, or something else, it reminds us that the vacuum hosts more than the particles we know. Quantum chromodynamics, the theory of the strong force, has a rich vacuum structure. Unlike the electromagnetic vacuum, the QCD vacuum contains fluctuating gluon fields and quark-antiquark pairs. Topological structures like instantons and sphalerons can change the vacuum's properties and affect the number of quark flavors. The QCD vacuum influences phenomena like the masses of hadrons and the suppression of certain symmetries. Understanding this complex vacuum helps physicists explain why protons and neutrons have the masses they do. It shows that vacua can vary in complexity, with some having intricate internal landscapes. Symmetry breaking is closely tied to the appearance of new particles. When a continuous symmetry is spontaneously broken, massless excitations called Goldstone bosons emerge. In superconductors, these excitations correspond to phonon-like modes. In particle physics, the breaking of chiral symmetry in QCD would produce massless pions if quarks were massless. Their small masses reflect the explicit breaking from quark masses. The Higgs mechanism is unusual because the would-be Goldstone bosons are eaten by gauge fields, giving them mass. Thus, by studying the vacuum's symmetry-breaking pattern, we can predict the spectrum of excitations. The vacuum not only supports fields, it determines which particles can exist. General relativity treats energy density and pressure differently. The vacuum energy has negative pressure, which causes repulsive gravity and accelerated expansion. This negative pressure arises from the equation of state of vacuum energy, where the pressure is equal to minus the energy density. In contrast, matter has positive energy density and negligible pressure on cosmic scales, leading to attractive gravity. Recognizing that pressure contributes to gravitational effects reminds us that the vacuum's equation of state is crucial in cosmology. It determines how quickly the universe expands and whether it will continue accelerating forever. Time itself may have connections to the vacuum. In canonical quantum gravity approaches, time disappears from the fundamental equations, suggesting that time might be emergent. If so, the vacuum's properties could play a role in how time emerges. The growth of entanglement and the accumulation of records may give rise to our perception of the passage of time. The vacuum sets the framework for this process, enabling interactions and decoherence. Exploring these ideas requires new theoretical tools, but they point to an intimate link between nothingness and temporality. As we prepare to move forward, it is worth pausing to reflect on the scale of what lies ahead. The vacuum is not just a footnote in physics. It is the medium through which all forces propagate, the source of subtle effects that shape atomic spectra and cosmic destiny. In the next part, we will build upon this foundation, exploring how matter clumps into stars and planets, how life emerges from chemistry, and how consciousness arises from biological structures. We will see that the journey from nothing to everything is continuous, filled with surprises and insights. By honoring the vacuum's hidden richness, we set the stage for deeper understanding. We often imagine nothing as a void, a blank canvas where no scene exists, but the human mind fills even an empty room with memories and moods. The idea of nothingness has long been a mirror for our own fears and hopes. To sit in quiet darkness is not to meet absence, but to hear the whisper of our own breath and heartbeat. Philosophers have wrestled with the concept, sometimes using nothing as a boundary to frame the essence of being. This subtle interplay between absence and presence hints that even in our imagination, a perfect nothing is elusive. Empty space always seems to invite stories, questions, and possibilities. The practice of physics treats nothing not as a pure emptiness, but as a medium rich with structure. When we ask what lies in a vacuum, we are not inquiring about an absolute absence. We are asking about the properties of the arena that hosts fields, particles, and their interactions. Scientists talk about the vacuum as a particular state of fields rather than an absence of everything. Even when there are no particles, the underlying fields still exist and have a state. In this sense, the vacuum is a special arrangement of the universe's building blocks, one that appears featureless to us precisely because it is the same everywhere and at all times, like a calm ocean whose surface hides a swirling undercurrent. The philosophical nothing differs from the physical vacuum by intent. When philosophers speak of nothing, they often mean the absence of all things, of any being whatsoever. In physics, we rarely talk about absolute non-existence. Instead, we consider a background state relative to which we measure disturbances. The scientific vacuum cannot be separated from the laws that describe it. The fields and the possibility of fluctuations are part of what we mean by space itself. This difference does not diminish the wonder of nothingness. Rather, it shows how language can carry multiple layers, bridging the poetic and the quantitative. Throughout history, cultures have found creative ways to express emptiness. In ancient creation myths, a primordial void often precedes the birth of the cosmos. In meditation practices, seeking a quiet mind is not about extinguishing thought completely, but about letting thoughts arise and fall without grasping. These diverse approaches reveal that emptiness is never truly empty, because the act of perceiving or conceptualizing it already imbues it with meaning. Our curiosity about what happens when we strip away all substance leads naturally into questions about the fundamental nature of reality. The journey from myth to measurement shows a continuity of wonder. When we look around, we see objects and feel surfaces. These impressions come from the interplay of forces carried by fields. To imagine those forces absent invites us to wonder about the very fabric that holds matter together. An empty table is still supported by the electromagnetic forces that keep its atoms arranged. Even a patch of interstellar space, apparently devoid of matter, is permeated by light from distant stars and by the gravitational influence of galaxies. The concept of nothing in physics is therefore a carefully defined baseline, not a state removed from all influence. Recognizing this helps us appreciate how a seemingly bland vacuum might conceal rich dynamics. Modern quantum field theory says that particles are excitations of fields that fill all of space. Each type of particle corresponds to its own field. Electrons, quarks, photons, neutrinos, and the rest are ripples on underlying seas. These fields are present everywhere, even in the absence of particles. Picture a tranquil pond that spans the universe. When the wind blows, ripples spread, and we see waves. In the calm, the water is still, but the pond is still there. Similarly, the calm vacuum contains the fields in their ground state. The existence of these fields means that emptiness is more like a medium than a void. They define what can happen when energy or matter enters the scene. To make this more vivid, think about the electromagnetic field, which supports light. In empty space, light propagates as a disturbance in this field. The field is present, even when no light is passing through. The existence of the field sets the rules for how disturbances travel. If we remove all photons, the field remains, sitting in its lowest energy state. The same is true for the Higgs field, which pervades space and gives mass to particles. Even when we cannot detect it directly, the Higgs field is everywhere. Like a mist we walk through without noticing. Because these fields are the fabric of reality, empty space is more like a stage with hidden scenery than a blank nothing. Quantum fields do not remain perfectly still. They are subject to the Heisenberg uncertainty principle, which tells us that certain pairs of measurable quantities cannot both be known to arbitrary precision. For a field, the value at a point and its rate of change are conjugate variables. The uncertainty principle implies that we cannot fix both. As a result, a field cannot sit motionless at a fixed value everywhere. Instead, it jitters around its ground state. This jitter is not caused by any external influence. It is intrinsic to the quantum nature of fields. These restless fluctuations mean that the vacuum is not quiet, but is alive with microscopic motion, even at absolute zero temperature. What we perceive as emptiness is therefore a dance of fields. Because fields are omnipresent, we can think of them as canvases on which the universe paints. When we say that a particle has appeared, we mean that the corresponding field has been excited in a certain region. The energy to create this excitation comes from interactions, much as pushing your hand into water creates ripples. In a vacuum, the fields have minimal excitations, but their potential to be disturbed is always there. The interplay between calm and excitement is central to understanding why the vacuum is interesting. It is not that something appears out of absolute nothing. Rather, the quiet stage supports the possibility of drama, and the actors are always ready to emerge when conditions allow. The Heisenberg uncertainty principle introduces a profound constraint on knowledge. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of our instruments. It is a fundamental property of nature. The principle applies not only to particles, but also to the values of fields. Trying to pin down a field's value exactly would inject enormous uncertainty into its rate of change, leading to violent oscillations. Conversely, allowing the field to fluctuate gently means accepting some fuzziness in its instantaneous value. This trade-off explains why zero-point fluctuations are unavoidable. The vacuum is restless, because perfect stillness would violate the uncertainty principle. To appreciate the uncertainty principle, imagine watching a tiny bead on a spring. In classical physics, the bead could sit motionless at the bottom of the spring's potential well. In quantum mechanics, the bead cannot have both a precise position and a precise momentum. If you try to squeeze the bead's position to a narrow region, you increase your uncertainty about its momentum. The bead will therefore wiggle. This wiggle is not due to any external push. It arises from the inherent indeterminacy in the bead's description. The same reasoning applies to every mode of vibration of a field. The ground state is not zero motion, but a delicate vibration. The interplay between measurement and disturbance underscores the mystery. When we measure a system, we interact with it. Shining light on a small particle can jostle it because the photons carry momentum. In everyday measurements, this disturbance is negligible, but at tiny scales, it becomes significant. The uncertainty principle tells us that this disturbance is not accidental, but intrinsic. To locate a particle precisely, one must use light of short wavelength, which carries high energy and momentum. That high-energy probe inevitably imparts momentum to the particle, altering its state. The measurement itself is part of the dynamic story, not a passive observation from outside. Zero-point energy is the energy that remains when a system is in its lowest possible state. In classical physics, a particle bound in a potential could have zero kinetic energy and sit quietly. Quantum mechanics forbids this complete stillness. For a simple harmonic oscillator, the zero-point energy corresponds to a certain fraction of the energy quantum associated with its natural frequency. This shift from zero energy to a finite ground state energy is a direct consequence of the uncertainty principle. Every vibrational mode has a minimal amount of energy that cannot be removed. When we consider all the modes of a field, the sum of their zero-point energies contributes to the vacuum energy, making the vacuum a reservoir of energy even in the absence of particles. Picture a vast landscape of springs and masses, one for every mode of a field. Each spring vibrates slightly in its ground state. Summing over all these tiny vibrations leads to an enormous theoretical energy density. However, only differences in vacuum energy are physically meaningful in most situations. For example, the energy difference between one configuration of conductors and another can produce measurable forces. The absolute value of the vacuum energy influences the expansion of the universe through the cosmological constant, but its precise value remains a deep mystery. The vacuum energy predicted by quantum field theory is vastly larger than what cosmological observations suggest. This discrepancy is one of the greatest puzzles in modern physics. Physicists calculate that if quantum fluctuations at all scales contribute to the vacuum energy, the resulting energy density would be many orders of magnitude larger than the dark energy density we infer from cosmic expansion. In simple estimates, the vacuum energy could be large enough to blow apart stars or warp spacetime beyond recognition. The fact that our universe is relatively calm indicates that the vacuum energy either cancels almost perfectly at most scales or is controlled by mechanisms we do not yet understand. This is known as the cosmological constant problem. Why is the vacuum energy so small compared to theoretical expectations? Some theories suggest unknown cancellations or new physics beyond the standard model to resolve this disparity. Despite the large theoretical energy, we can measure differences in vacuum energy in controlled settings. One famous example is the Casimir effect, a force that arises between two uncharged, parallel metal plates placed very close together in a vacuum. In this setup, the boundary conditions restrict the types of electromagnetic field modes that can exist between the plates. In the space outside the plates, more modes are allowed. The difference in zero-point energy between the inside and the outside exerts a force that pushes the plates together. This attractive force is tiny but measurable. It demonstrates that manipulating the vacuum's structure can produce tangible effects. The Casimir effect is sometimes poetically described as a whisper from the vacuum, reminding us that empty space is not inert. A mechanical explanation of the Casimir effect helps demystify it. Consider three large plates, two fixed plates at a distance, and a third movable plate between them. The region between the movable plate and one fixed plate is narrow, so only electromagnetic waves with certain wavelengths fit. In the larger region beyond the movable plate, a broader range of wavelengths is allowed. When the movable plate shifts slightly, the energy associated with modes in the narrow region increases significantly, while many modes in the larger region decrease only slightly. The net change in energy is negative, leading to an attractive force that pulls the plates together. This force does not come from sucking energy from nothing. It arises from the way boundary conditions alter the spectrum of vacuum fluctuations. Casimir forces are not limited to parallel plates. Similar effects appear in many systems where boundary conditions modify the vacuum. For example, dielectric materials separated by a small gap experience forces due to the quantum vacuum. At very small scales, these forces contribute to the adhesion of nanostructures. In some biological systems, tiny Casimir-like forces can influence molecular interactions. Although these forces are weak compared to electromagnetic or chemical forces, they demonstrate that the vacuum can mediate subtle interactions. Researchers continue to explore whether such effects can be harnessed in micromechanical devices or contribute to friction at small scales. However, the energy involved is tiny and cannot be used to extract free work from the vacuum. Quantum field fluctuations are often described using the language of virtual particles. These are transient excitations that pop in and out of existence, borrowing energy for a short time before disappearing. The term virtual particle can be misleading because the underlying reality is a fluctuating field rather than discrete particles popping in and out. Still, the concept is useful in calculations. Virtual particles contribute to phenomena such as the Lamb shift, where the energy levels of electrons in hydrogen are slightly different from those predicted by simple models. They also affect the magnetic properties of particles and cause coupling constants to run with energy scale. Precise experiments confirm these theoretical predictions, giving us confidence that quantum fluctuations are real features of the world. Virtual particles do not violate energy conservation, because the energy borrowed is repaid within a time allowed by the uncertainty principle. The product of the energy borrowed and the time borrowed must satisfy a relationship similar to the uncertainty between position and momentum. The larger the energy borrowed, the shorter the time the fluctuation can persist. This means that short-lived, high-energy fluctuations can momentarily affect interactions, but cannot be observed directly. What we measure are their cumulative effects on observables, like particle masses and forces. This subtle interplay between the unseen and the measurable underlines the beauty of quantum theory. It provides a mathematical framework to predict how invisible fluctuations shape observable reality. Fluctuations also occur in the gravitational field. Though we do not yet have a complete quantum theory of gravity, some speculative ideas suggest that at extremely small scales, spacetime itself may foam with temporary wrinkles. These fluctuations would be suppressed at larger scales, but might have played a role in the early universe. During cosmic inflation, quantum fluctuations in the inflaton field could have been magnified, seeding the density variations that later grew into galaxies and clusters. Observations of the cosmic microwave background show a pattern of temperature anisotropies that fit the statistical properties expected from quantum fluctuations stretched to cosmic scales. Though we lack a direct citation here, this narrative connects the micro and the macro, hinting at how the universe's large-scale structure may have originated in the whisper of quantum fluctuations. The term virtual underscores that these fluctuations are not particles in the same sense as a real photon detected by a sensor. They are mathematical constructs representing temporary departures from the vacuum state. In Feynman diagrams, virtual particles appear as internal lines that connect interactions. They are integrated over all possible energies and times, representing the sum over histories. This calculus yields finite corrections to scattering amplitudes, demonstrating how the vacuum shapes interactions, even when we cannot see the excitations directly. By computing these corrections, physicists can predict the outcomes of experiments with remarkable precision, reinforcing the view that the vacuum is an active participant in every process. When we ask whether virtual particles are real, we face a philosophical question. If reality is defined by direct detection, then virtual particles do not qualify. If reality includes anything that has measurable effects, then virtual particles are as real as gravitational potential energy or wave functions. Their existence and properties cannot be captured by classical intuition, but their influence is undeniable. The fact that we can compute and measure their effects invites us to expand our understanding of what counts as real. In the quantum world, things can be both intangible and profoundly consequential. The act of measurement introduces another layer of complexity. When we measure a quantum system, we cannot escape interacting with it. This interaction inevitably disturbs the system, blending our knowledge and the system's history. The measurement problem asks how a definite outcome arises from the probabilistic wave function. Different interpretations offer varied answers. Some propose that the wave function collapses when observed. Others suggest that all possibilities exist in a multiverse, and still others emphasize the role of information and decoherence. What all interpretations agree on is that the observer cannot be separated from the observed. The question is not just what happens in the vacuum, but how we, as embedded beings, access its secrets. On the practical side, measuring tiny effects requires ingenious techniques. For example, to detect the Casimir force, experimentalists place metal plates a few micrometers apart and measure the slightest movement. To observe the Lamb shift, spectroscopists use lasers and microwaves to probe atomic transitions with extraordinary precision. Each measurement pushes the limits of technology and human patience. Behind every data point lies countless hours of calibration, noise reduction, and theoretical modeling. The interplay between experiment and theory is what turns abstract concepts like zero-point energy into tangible knowledge. It is through measurement that the invisible becomes part of our shared reality. Measurement also raises questions about meaning. The word real often implies something solid and permanent. But at the quantum level, properties are relational and contextual. An electron's spin is not an intrinsic direction until it is measured. Before measurement, the electron exists in a superposition, a combination of possibilities. After measurement, we record a definite value. What changed? Decoherence offers one explanation. When a quantum system interacts with its environment, the interference between different possibilities becomes practically unobservable. The system's wave function becomes entangled with countless degrees of freedom, effectively selecting one outcome for all practical purposes. In this view, measurement does not collapse reality, but correlates it with the environment. Decoherence arises because quantum systems are rarely isolated. Each particle, atom, or photon interacts with surrounding fields, thermal radiation, and other particles. These interactions cause the coherence among different components of the wave function to dissipate into the environment. The environment carries away information about the system's phase relationships, leaving behind what looks like a classical probability distribution. Gravity may also play a role in decoherence. Some proposals suggest that the gravitational field, being universal and difficult to shield, contributes a constant background that entangles with quantum systems. Although this remains speculative, it highlights how deeply interconnected all aspects of physics are when we think about the emergence of the classical world. The concept of decoherence does not fully solve the measurement problem. While it explains why interference terms become negligible, it does not single out one particular outcome. In many worlds' interpretations, all outcomes occur in different branches of the wave function, with decoherence ensuring that the branches do not interfere. In other interpretations, a genuine collapse is introduced on top of decoherence. Despite these philosophical debates, decoherence has practical implications. It sets limits on how long quantum information can be preserved. Quantum computing, for example, relies on keeping qubits coherent for as long as possible. Environmental noise leads to decoherence, causing errors. Understanding and controlling decoherence is therefore essential for advancing quantum technologies. In thinking about decoherence, we must remember that the universe as a whole evolves unitarily. If we could observe the entire universe, no coherence would ever be lost. Decoherence arises when we partition the universe into a system and an environment, and ignore the environment's degrees of freedom. This partition is practical, but not fundamental. The lost coherence is not destroyed, but is hidden in correlations with the environment. This view underscores that classical reality is an effective description arising from the vastness of the environment. The boundary between quantum and classical is not sharp, but emerges from our limited ability to track all interactions. The concept of records is crucial here. To say that an event happened, we need a persistent record. In our world, records are stored in the positions of atoms, the states of neurons, or bits on a hard drive. Decoherence turns fleeting quantum possibilities into robust classical records by correlating them with many degrees of freedom. Once the correlation spreads, reversing it would require impossible coordination. That is why we rarely witness a broken glass unbreaking or a cloud of smoke reforming into a cigar. The arrow of time emerges from the accumulation of records, which in turn arises from the entangling nature of interactions. The vacuum may be full of fluctuations, but the macroscopic world is full of records. The scale of these processes can vary dramatically. In a controlled lab, we might isolate a few atoms for milliseconds, preserving their coherence long enough to perform computations or tests. In cosmic settings, decoherence can occur across light years. The cosmic microwave background carries imprints of quantum fluctuations that have decohered into classical density variations. The interplay between micro and macro emphasizes that nothingness and somethingness are not separate domains, but parts of a continuum. The same physical laws govern both, but their manifestations depend on scale and context. Understanding how quantum possibilities become classical realities is as important for cosmology as it is for quantum information science. On the largest scales, the universe is dominated by dark energy. Observations show that about 2/3 of the total energy density of the cosmos comes from this mysterious component. Dark energy causes the expansion of the universe to accelerate. One simple explanation is that dark energy is the energy of empty space itself, the cosmological constant originally introduced by Einstein. If this is true, the vacuum energy we measure in the lab is related to the same vacuum energy that drives cosmic acceleration. Yet the smallness of the cosmological constant compared to theoretical predictions remains puzzling. Understanding dark energy requires us to connect the quantum vacuum with the universe's evolution. The discovery of cosmic acceleration came at the end of the 20th century, when astronomers measured the brightness of distant supernovae and found that the universe's expansion was speeding up rather than slowing down. Additional evidence from the cosmic microwave background and the distribution of galaxies supports this conclusion. Because the expansion was slower in the past, matter had time to clump into galaxies and stars before dark energy began to dominate. Today, dark energy is the largest component of the universe, while ordinary matter makes up only a small fraction. This unexpected imbalance forces us to rethink our assumptions about energy in the cosmos. The vacuum, once thought inert, shapes the destiny of everything. The amount of dark energy and its properties influence the ultimate fate of the universe. If the cosmological constant remains constant, the expansion will continue accelerating, leading to a cold, lonely future in which galaxies recede beyond each other's horizons. If dark energy evolves over time, as in some models of quintessence, the fate could be different. In all cases, dark energy reveals that nothingness has dynamic, tangible consequences. The vacuum is not only active at microscopic scales, it drives cosmic evolution. This link between the smallest and the largest illustrates the unity of physics. To understand why there is something rather than nothing, we must consider both the restless quantum vacuum and the expanding universe it inhabits. The mismatch between the vacuum energy predicted by quantum field theory and the observed cosmological constant is breathtaking. Theory suggests a vacuum energy density many orders of magnitude larger than what we observe. Yet somehow, the net effect on cosmic expansion is tiny. One possibility is that unknown cancellations occur among the contributions of different fields. Another is that our understanding of gravity and the vacuum is incomplete. Some theories propose that the vacuum energy is exactly zero due to asymmetry and that dark energy is something else entirely. Others suggest that anthropic arguments in a multiverse may be needed. Only in regions with a small cosmological constant can galaxies form and observers emerge. The debate continues, highlighting the deep connections between particle physics, cosmology, and philosophy. The concept of scale extends beyond the cosmological constant problem. In a particle accelerator, we probe the vacuum at energies billions of times higher than those in everyday life. The vacuum's structure changes with energy, causing forces like the strong interaction to weaken at higher energies. This running of couplings is a direct consequence of quantum fluctuations. At cosmic scales, the vacuum interacts with gravity, causing space to expand. The same vacuum that resists perfect stillness in a small cavity also pushes galaxies apart. The unity of these phenomena underlines that scale is not a barrier separating different kinds of nothingness. It is a lens through which the same underlying reality manifests differently. Philosophically, the idea that the universe came from nothing often conjures images of sudden creation out of absolute emptiness. However, modern cosmology suggests that the early universe was a hot, dense state filled with energy and fields. When we trace cosmic expansion backward in time, we reach a point where classical descriptions break down and quantum gravity becomes important. In some models, the universe emerges from a quantum fluctuation in a pre-existing vacuum. In others, the universe undergoes cycles or bounces. The idea of creation from nothing is therefore more subtle than a simple moment of genesis. It involves the interplay of quantum mechanics, general relativity, and the structure of the vacuum. While we lack a definitive answer, the story points toward a deep unity of physics. In everyday experience, the vacuum does not seem to influence our lives. We sit on chairs, breathe air, and rarely consider the emptiness between atoms. Yet all these experiences rely on the vacuum. The electromagnetic forces that hold atoms together arise from photons propagating through the vacuum. The masses of particles come from their interactions with the Higgs field. The colors we see and the warmth we feel depend on how the vacuum transmits light and heat. Even the sense of time's flow, through the increase of entropy and the accumulation of records, can be traced back to interactions in the vacuum. Recognizing the vacuum's role enriches our appreciation of the mundane. Nothingness is the stage on which everything unfolds. As we reach the end of this exploration of nothingness, we find ourselves standing at a doorway rather than a conclusion. We have seen that what we call empty space is a seething field of activity. We have learned that uncertainty prevents perfect stillness, that zero-point energy hums quietly beneath matter, and that virtual fluctuations leave real traces. We have glimpsed how boundary conditions can make the vacuum push things together, and how measurement entangles observers with the observed. We have considered how decoherence turns possibilities into records, and how dark energy accelerates the cosmos. Each insight opens new questions. The door ahead leads to the next part of our journey: how structures, galaxies, and consciousness arise from this dynamic nothing. The story of the quantum universe is just beginning. Our contemplation of emptiness can even encompass black holes, where gravity warps spacetime so strongly that not even light can escape. According to quantum theory, the vacuum near an event horizon is unstable. Virtual particle pairs form as usual, but one partner may fall into the black hole while the other escapes as Hawking radiation. Over immense timescales, a black hole can evaporate by converting its mass into these photons and particles. This process is an example of how the vacuum interacts with gravity to create energy. The seeming paradox of something emerging from nothing hints at deeper unities yet to be understood. Magnetars and other extreme astrophysical objects push the vacuum to its limits. Their magnetic fields are strong enough to polarize the vacuum, making it behave like a birefringent medium that splits light into different polarizations. Observations of polarized light from neutron stars probe this effect. Similarly, gamma rays from particle accelerators replicate cosmic conditions, letting us test how the vacuum responds to enormous forces. These studies show that the vacuum is not a passive backdrop, but an active participant in the universe's most violent events. In laboratories, researchers explore dynamic versions of the Casimir effect by rapidly moving mirrors or modulating superconducting circuits. The changing boundary conditions shake the vacuum, converting zero-point fluctuations into real photons. Such experiments detect motion-induced radiation, a subtle form of vacuum friction. Even though the energy extracted is tiny, it demonstrates that accelerating through a vacuum or changing its geometry can create particles. These experiments are glimpses of a deeper principle. The vacuum responds to motion and shape in ways that are only now being uncovered. Philosophers and physicists debate the ontological status of these virtual excitations. Are they real, if they cannot be isolated directly? The measurement problem and decoherence suggest that reality is relational. What exists depends on interactions that create records. The vacuum's fluctuations are therefore potentialities awaiting an interaction. When we measure them through an atomic transition or a Casimir force, they become part of our classical world. When unmeasured, they remain part of the quantum substrate. This perspective dissolves the boundary between being and non-being into a continuous spectrum of possibilities. Artists have long embraced emptiness as a creative tool. In painting, the negative space around an object defines its form. In music, silence between notes shapes rhythm and meaning. Similarly, in architecture and gardens, empty spaces guide movement and perception. These uses of nothingness mirror the physical vacuum's role. The quiet intervals give shape to the experience. Recognizing this parallel deepens our appreciation of the interplay between structure and absence, both in art and in physics. It reminds us that emptiness is not the absence of content, but the context that allows content to emerge. Meditative traditions also explore nothingness, describing states of mind where thought and self recede. Contemplatives report experiences of clarity, spaciousness, and connection that arise when mental chatter subsides. These practices do not aim to annihilate thought, but to reveal a background awareness that was always present. The analogy with the quantum vacuum is imperfect, yet evocative. Just as fields and fluctuations underlie matter, awareness and potential underlie experience. Exploring these parallels invites a more holistic view of reality, one that honors both science and inner exploration. We have traveled from philosophical musings to the edge of black holes, from the early universe to the lab bench, always guided by the question of what it means for something to emerge from nothing. We have seen that the vacuum is rich and structured, that emptiness is dynamic, and that measurement weaves potential into actuality. The next part of our journey will examine how this restless nothing gives rise to structure, how fields condense into particles, how galaxies coalesce from fluctuations, and how life and consciousness arise in a universe born of quantum possibility. Our exploration continues, always with wonder and curiosity. Different gravitational wave detectors are sensitive to different frequency bands, offering complementary views of the gravitational wave background. Pulsar timing arrays monitor the arrival times of radio pulses from millisecond pulsars to detect waves with periods of years, while ground-based detectors like LIGO and Virgo listen for kilohertz waves from stellar mass mergers. The future space-based observatory, LISA, will bridge these bands, targeting waves from massive black hole mergers and galactic binaries. Together, these instruments map the gravitational spectrum, revealing how the vacuum vibrates across scales. The cosmic microwave background is nearly a perfect blackbody, but small deviations in its spectrum could reveal energy injections in the early universe. Spectral distortions arise from processes like the damping of acoustic waves, decaying particles, or cosmic reionization, altering the distribution of photon energies. Upcoming missions aim to measure these distortions with unprecedented sensitivity, probing processes that occurred when the universe was less than a few months old. Detecting such distortions would provide a new diagnostic of the vacuum's history and of energy releases beyond the reach of other observations. Supernova explosions release an immense flux of neutrinos that carry away most of the gravitational binding energy of the collapsing core. Observations of neutrinos from supernova 1987 are confirmed theoretical predictions and demonstrated that neutrinos travel unimpeded through dense matter and vacuum alike. Future detections of supernova neutrino bursts will refine models of stellar collapse and nucleosynthesis. They also provide tests of neutrino properties, such as their masses and possible exotic interactions, bridging astrophysics and particle physics. High-energy neutrino observatories like IceCube and Antares detect neutrinos produced in cosmic accelerators, such as active galactic nuclei and gamma-ray bursts. These particles travel vast distances, crossing cosmic voids and penetrating the Earth, carrying information about their sources and the intervening vacuum. Correlating neutrino detections with electromagnetic or gravitational wave signals enables multi-messenger studies of energetic phenomena. Through neutrino astronomy, we use the ghostly messengers to probe the universe's most extreme environments. Magnetic fields shape the dynamics of cosmic plasmas, influence star formation, and guide the propagation of charged particles. The origin of these fields remains an open question, with possibilities ranging from primordial generation during inflation to amplification by dynamos in galaxies. Magnetohydrodynamics describes the interplay between fluids and magnetic fields, revealing phenomena like jets, accretion disks, and solar flares. Understanding cosmic magnetism sheds light on how the vacuum interacts with charged matter on multiple scales. Precise measurements of time and frequency have become powerful tools for probing gravitational physics and cosmology. Atomic clocks achieve extraordinary stability and can detect tiny variations in the gravitational potential as they move through space. Networks of clocks on Earth and in space may one day monitor gravitational waves or test the constancy of fundamental constants. These chronometers act as delicate sensors of the vacuum structure and of any ripples that pass through it. Axions were originally proposed to solve the strong CP problem in quantum chromodynamics, but they have since become leading candidates for dark matter. If axions exist, they could form a cold condensate, filling the vacuum with a coherent field. Searchers exploit their coupling to electromagnetic fields, using resonant cavities, haloscopes, and helioscopes to convert axions into photons. Discovering axions would reveal a new component of the vacuum that influences both particle physics and cosmology. The universe may host a stochastic background of gravitational waves, arising from the superposition of many unresolved sources. Primordial gravitational waves from inflation or phase transitions would contribute to this background, as would astrophysical events like compact binary mergers. Upcoming detectors aim to measure this diffuse hum by looking for correlated signals across multiple instruments. Detecting the gravitational wave background would open a new window onto processes that shaped the vacuum in the early universe. Future telescopes and surveys promise to refine our picture of the cosmos with unprecedented detail. Facilities like the Square Kilometre Array, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory will map vast volumes of space, capturing galaxies, supernovae, and transient events. These observations will test models of dark energy, probe modifications of gravity, and search for signatures of new physics. Each new survey is like a deeper breath into the vacuum, revealing structures and patterns that inform our theories. Some theories envision that fundamental couplings vary across extra dimensions or are influenced by the dynamics of brains. In such scenarios, the apparent constants in our four-dimensional world arise from fields in higher dimensions, settling into specific configurations. If these configurations change over cosmic time, couplings could slowly drift, leaving imprints on cosmological observations and precision measurements. Exploring such possibilities blurs the line between particle physics and cosmology, linking the vacuum to the geometry of hidden dimensions. Observations of gamma-ray structures like the Fermi bubbles above and below the Milky Way's plane hint at energetic processes in our galaxy's past. These giant lobes could result from outflows powered by the central black hole, or by winds from intense star formation. High-energy photons travel through the interstellar vacuum, interacting with magnetic fields and ambient radiation. Studying these structures provides clues to the interplay between astrophysical activity and the vacuum environment. Testing general relativity with high precision remains a priority, as any deviation could signal new interactions or fields. Experiments ranging from lunar laser ranging to satellite measurements probe the equivalence principle and the inverse square law. Modifications of gravity might arise from extra dimensions, scalar tensor theories, or massive gravity, each altering the vacuum structure. Continued scrutiny helps constrain these alternatives and reinforces our understanding of spacetime and the vacuum. Reheating might proceed through alternative mechanisms, such as the curvaton scenario, where a secondary field generates curvature perturbations and reheats the universe. In other models, moduli fields associated with extra dimensions or supersymmetry play a role in reheating and can dominate the energy density before decaying. These possibilities alter the relation between the inflaton and the observable perturbations and can affect the spectrum of particles produced. Exploring different reheating scenarios expands the landscape of early universe dynamics. Mirror matter theories propose the existence of a parallel sector with particles and forces mirroring those of the standard model. Such twin sectors could interact with our world only through gravity or through a portal like the Higgs. If mirror matter exists, it could constitute some of the dark matter and influence structure formation. Investigating these hidden sectors challenges our conception of the vacuum, inviting speculation that what we perceive as empty space may harbor unseen worlds. Gravitational waves generated during inflation could leave a signature in the polarization of the cosmic microwave background. The B-mode pattern, characterized by twisting polarization vectors, arises from tensor perturbations that propagate as ripples in space-time. Detecting these patterns would provide direct evidence of inflationary gravitational waves and probe the energy scale of inflation. Sensitive experiments target these subtle signals amid foreground emissions and lensing effects. Primordial black holes may have formed from overdensities in the early universe, collapsing regions where the fluctuations were large enough to overcome pressure. Such objects would have masses ranging from tiny to stellar, depending on when they formed. If they exist, they could contribute to dark matter, seed supermassive black holes, or evaporate via Hawking radiation. Observational limits from microlensing, gravitational waves, and the cosmic microwave background constrain their abundance. The cosmic neutrino background, a relic from the first seconds, offers another window into early conditions. Detecting it would complement studies of the cosmic microwave background and improve constraints on neutrino masses. Techniques include capturing neutrinos via beta decay in tritium or observing coherent neutrino scattering. These efforts underscore how the vacuum's earliest excitations leave traces that persist to the present. Vacuum energy sits at the heart of the cosmological constant problem. An enormous gap between theoretical estimates and observed values. Supersymmetry, if realized in nature, could cancel large contributions by pairing bosons and fermions. Yet no evidence for supersymmetric particles has been found at current collider energies. This absence challenges straightforward solutions and motivates alternative ideas. The fine-tuning required remains one of the deepest puzzles connecting particle physics to cosmology. Models with extra-spatial dimensions propose that our four-dimensional universe is a slice of a higher-dimensional spacetime. In brain-world scenarios, standard model particles are confined to a three-dimensional brain, while gravity propagates in additional dimensions. These frameworks can modify the behavior of gravity at short distances and affect cosmology. Experiments testing gravity at millimeter scales and searches for Kaluza-Klein excitations probe such possibilities. Quantum gravity aims to reconcile general relativity with quantum mechanics, offering potential insights into the structure of the vacuum at the Planck scale. Loop quantum gravity explores a granular spacetime built from spin networks, while string theory proposes that fundamental entities are one-dimensional strings whose vibrations manifest as particles. Both approaches seek a consistent description of spacetime and matter at the smallest scales. Their implications for cosmology remain an active area of research. The holographic principle posits that the information contained in a volume of space can be encoded on its boundary. In the ADS/CFT correspondence, a gravity theory in a higher dimensional space is equivalent to a conformal field theory on its boundary. This duality has illuminated the behavior of strongly coupled systems and black holes, suggesting that spacetime itself may emerge from more fundamental degrees of freedom. Such ideas reinterpret the vacuum as a holographic projection rather than a static backdrop. Non-commutative geometry modifies the structure of space by allowing coordinates to fail to commute, leading to uncertainty relations between positions. Incorporating this notion into field theories can regularize divergences and alter vacuum properties at small scales, while speculative, non-commutative models highlight the possibility that geometry itself may be quantized. Exploring these possibilities may shed light on the nature of the vacuum near the Planck scale. The anthropic principle often enters discussions about vacuum energy and other parameters. It suggests that only those regions of the multiverse with values conducive to the formation of complex structures will host observers. This selection effect could explain why the cosmological constant is small, or why particle masses take the values we observe. Though controversial, the anthropic reasoning reflects our desire to connect the vacuum's properties with the conditions for life. Polarization measurements of the cosmic microwave background reveal not only B-mode patterns, but also E-mode patterns that trace density fluctuations and gravitational lensing. Cross-correlations between temperature and polarization maps improve constraints on cosmological parameters and the ionization history of the universe. Future experiments aim to reduce noise and foreground contamination to approach the sensitivity needed to detect primordial B modes. Achieving this goal would confirm key predictions of inflation and further illuminate the vacuum's early dynamics. Large cosmic voids occupy vast regions between filaments and clusters, making up much of the volume of the universe. Though mostly empty, voids contain galaxies and dark matter at low densities and serve as laboratories for testing gravity. Their dynamics are sensitive to dark energy and modified gravity models. Studying void shapes, growth, and integrated Sachs-Wolf effects provides complementary constraints on cosmological parameters. High-energy cosmic rays bombard Earth from space, reaching energies far beyond those produced by human-made accelerators. Their origins remain partly mysterious, involving supernova remnants, active galactic nuclei, or perhaps decay of exotic particles. These particles travel through interstellar and intergalactic magnetic fields, sampling the vacuum along their journey. Studying their spectra and composition helps reveal the astrophysical processes and conditions that accelerate them. The epoch of rayonization marks the transition from a neutral to an ionized intergalactic medium, driven by the first stars and galaxies. Observations of the 21-centimeter line of hydrogen and distant quasars help map this era. The timing and duration of rayonization inform models of structure formation and the feedback processes that regulate star formation. This period also marks a transformation of the cosmic vacuum, as radiation from luminous sources interacts with gas. Discoveries of exoplanets in the habitable zones of their stars have broadened our view of where life might arise. The habitability of a planet depends on its distance from the star, atmospheric composition, and stellar stability. Fundamental constants influence the chemistry that underlies biology. Even slight variations might inhibit the formation of complex molecules. Linking the vacuum's properties to the conditions for life invites reflections on the universality and contingency of our existence. The possibility of sterile neutrinos that do not interact via the weak force, offers another extension of the standard model. These hypothetical particles could contribute to dark radiation or help explain anomalies in neutrino experiments. If they exist, they would change the energy density of the early universe and leave imprints on the cosmic microwave background and structure formation. Ongoing experiments search for hints of their presence. Additional relativistic degrees of freedom, sometimes called dark radiation, could manifest as changes in the effective number of neutrino species. Measurements of the cosmic microwave background and nucleosynthesis constrain this number, but small deviations remain possible. Such radiation might arise from light particles in hidden sectors or from non-standard decoupling histories. Detecting or constraining dark radiation would inform our understanding of the vacuum's content. Cross-correlations between different cosmological surveys, such as combining weak lensing with galaxy clustering or cosmic microwave background lensing with galaxy surveys, enhance sensitivity to fundamental parameters. These synergistic analyses reduce systematic errors and break parameter degeneracies. They exemplify how observations can be woven together to extract maximal information about the vacuum and its evolution. Collaboration across multiple observational platforms reflects the interconnected nature of cosmic phenomena. Multi-field inflation models involve more than one scalar field driving the exponential expansion. Interactions among the fields can generate non-Gaussian fluctuations and rich reheating dynamics. In such scenarios, preheating may involve fields decaying into different sectors and producing specific particle spectra. The patterns left in the cosmic microwave background could reveal clues about the number and nature of the fields involved. The interplay between astrophysical observations and particle physics experiments continues to refine our understanding of the vacuum. Measurements of galaxy clustering inform constraints on neutrino masses, while collider experiments probe the properties of the Higgs boson and search for new particles. Cosmic surveys constrain the sum of neutrino masses, complementing laboratory oscillation experiments. This interplay underscores how insights from the largest and smallest scales converge to illuminate the same underlying vacuum. All of these avenues of inquiry remind us that the quest to understand the quantum universe is ongoing. Each discovery raises new questions and opens uncharted territories of exploration. Our narrative remains open-ended, echoing the unfinished symphony of the cosmos. As we continue onward, the invisible ground beneath our reality beckons with mysteries yet to unfold. Renormalization is one of those subtle concepts that emerges naturally from this landscape. At high energies, the vacuum looks different than it does at low energies, and the strengths of interactions flow like streams running down a mountain. Physicists learn to treat infinities by redefining parameters such that predictions remain finite and meaningful at each scale. This renormalization group flow reveals that the vacuum is not a fixed stage, but an evolving fabric whose properties depend on the energy at which we probe it. Interactions between fields are rarely simple, and self-interactions can warp the geometry of the vacuum. Fields can interact with themselves in non-linear ways that modify their potentials and lead to rich dynamics. These non-linearities mean that excitations are not independent ripples, but influence one another through the medium they share. Understanding these self-couplings is essential to grasp how the vacuum organizes itself and transitions between phases. Symmetries intimately tie to gauge invariance and conservation laws. Gauge symmetries arise when certain field transformations leave the physics unchanged, introducing a redundancy in our description. The photon, gluons, and other force carriers emerge as gauge bosons associated with these symmetries, mediating interactions in a way consistent with conservation laws. This gauge structure ensures that our mathematical descriptions reflect deeper principles rather than superficial choices. Not all symmetries survive quantization unscathed. Anomalies reveal that classical invariances can break when the quantum vacuum is considered. Anomalies arise when the regularization needed to handle infinities fails to preserve all symmetries, leading to new effects like the decay of the neutral pion into two photons. These quantum corrections highlight the delicate balance between symmetry and the underlying degrees of freedom. They remind us that the vacuum can subtly influence processes that appear forbidden in simpler descriptions. Topological features of field configurations add yet another layer of richness. Solitons, instantons, and skyrmions are stable patterns that owe their existence to the topology of the vacuum rather than energy minimization alone. In cosmology, defects such as cosmic strings could form during phase transitions when symmetry breaks in different regions, leaving trapped energy along lines or walls. These structures could generate gravitational waves or seed structure on large scales, offering potential observational windows into the early vacuum. Even in the absence of particles, the vacuum seethes with zero-point fluctuations. These fluctuations manifest in observable effects, like the Casimir force between uncharged conducting plates and the Lamb shift in atomic spectra. Both arise from the interaction of matter with the background of virtual photons and other fields. Such phenomena demonstrate that so-called empty space influences the behavior of matter through subtle quantum effects. Particle-antiparticle pairs can momentarily emerge from the vacuum and annihilate, a process sometimes described in terms of virtual particles. In strong electric fields, This can lead to observable pair creation, as in the Schwinger effect. The early universe was filled with such buzzing pair creation and annihilation, and a slight imbalance between matter and antimatter left the residue we see today. These fleeting pairs highlight how the vacuum is a dynamic medium rather than a passive backdrop. The thermal radiation permeating space is not limited to photons. The universe is also bathed in a relic sea of neutrinos, decoupled when it was only seconds old. These cosmic neutrinos remain difficult to detect because of their weak interactions. Yet they carry information about the early vacuum and the conditions that prevailed during nucleosynthesis. Future experiments hope to capture this faint whisper, adding another piece to the cosmic puzzle. Quantum information theory casts the vacuum in a new light by emphasizing entanglement and coherence. The entanglement between regions of space reflects correlations in the quantum fields that fill the vacuum. Concepts like entanglement entropy measure how information is shared across boundaries, linking the geometry of space to quantum correlations. This perspective suggests that spacetime itself may emerge from patterns of entanglement, deepening our appreciation of the vacuum's role in the architecture of reality. Observational cosmology employs diverse techniques to probe the vacuum and its imprints. Weak gravitational lensing maps the distribution of matter by measuring the subtle distortion of galaxy shapes by intervening mass. Direct detection of gravitational waves opens a window onto violent processes that stir the vacuum, such as merging black holes or phase transitions in the early universe. Experiments sensitive to the cosmic neutrino background, though challenging, would further illuminate the thermal history of the vacuum. Accelerated observers perceive the vacuum differently than inertial ones. According to the Unruh effect, an observer accelerating through empty space will detect a thermal bath of particles, with a temperature proportional to the acceleration. This surprising prediction arises from the interplay between quantum fields and the definition of particles, which depends on the observer's motion. It underscores that the notion of a vacuum is not absolute, but relative to the state of motion of the observer. Black holes provide another arena where quantum fields interact with curved spacetime. Stephen Hawking showed that black holes are not entirely black, but radiate like hot objects, slowly losing mass through Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where one member of a pair of virtual particles falls into the black hole while the other escapes. The result is that even the most extreme gravitational environments cannot suppress the restless vacuum. The interplay between gravity and quantum fields can be studied in analog systems created in laboratories. Experiments with flowing fluids, optical fibers, or Bose-Einstein condensates can mimic the behavior of horizons and Hawking radiation. These analog gravity systems provide tangible platforms to explore phenomena that would otherwise be inaccessible. They show that concepts we associate with cosmic scales can manifest in tabletop settings, connecting the cosmic to the everyday. Symmetry breaking does not belong exclusively to high-energy physics. Condensed matter systems exhibit quantum phase transitions, where the vacuum changes character at zero temperature. Transitions between superconducting and insulating phases, or between different magnetic orders, provide analogies to cosmological phase changes. Studying such systems helps illustrate how collective behavior arises from microscopic rules, and how the structure of the vacuum controls the emergence of excitations. Some questions require non-perturbative methods, as the usual expansion in small couplings fails at strong interaction strength. Lattice gauge theories discretize spacetime into a grid, enabling numerical simulations of quantum fields, like quantum chromodynamics. These calculations reveal how quarks and gluons confine into hadrons, and how the vacuum condensates of quark-antiquark pairs contribute to the mass of visible matter. The results emphasize how the vacuum shapes even the stability and masses of everyday particles. Dark energy may take forms more complex than a simple cosmological constant. Models of quintessence posit a slowly rolling scalar field whose potential energy drives acceleration. Unlike a constant vacuum energy, quintessence evolves over time, potentially affecting the expansion history and structure growth. Observations of supernovae, large-scale structure, and the cosmic microwave background constrain these models, searching for subtle departures from a constant equation of state. The dark sector could also contain particles beyond the standard model. Weakly interacting massive particles and axions are two leading candidates, each with different experimental signatures. Direct detection experiments seek to observe dark matter scattering off nuclei, while axion searches exploit its coupling to photons. Discovering such particles would reveal new fields that may have influenced the early vacuum and its transitions. Neutrino oscillations demonstrate that neutrinos have mass and change flavors as they propagate. This phenomenon implies physics beyond the original standard model and may connect to the mechanism that generates the matter-antimatter asymmetry. If heavy neutrinos existed in the early universe, their decays could produce a lepton asymmetry, later converted to a baryon asymmetry. Thus, the ghostly neutrino could hold the key to understanding why we are here. Topological defects, like cosmic strings, could arise from symmetry breaking in the early universe. These one-dimensional objects would carry enormous energy and might generate gravitational waves or lens background radiation. Searches for the signatures of cosmic strings in the cosmic microwave background and gravitational wave data place limits on their abundance. Though not yet detected, such relics would offer direct evidence of the vacuum's structure during phase transitions. The remnants of sound waves in the primordial plasma, known as baryon acoustic oscillations, continue to inform cosmology. They provide a standard ruler for measuring cosmic distances and have been observed in galaxy surveys and the Lyman alpha forest. Combining this information with other probes refines our understanding of the expansion rate and the properties of dark energy. The concordance between independent measurements strengthens confidence in our model of the vacuum's influence on cosmic evolution. Magnetic fields are ubiquitous in the universe, yet their origin remains a puzzle. Astrophysical dynamos can amplify seed fields, but some primordial magnetogenesis may have occurred during inflation or phase transitions. If the vacuum allowed the generation of small magnetic fields in the early universe, these seeds could be stretched and amplified over time. Observations of intergalactic magnetic fields offer clues to these early processes. Investigations of time-varying fundamental constants test whether the laws of physics are truly immutable. Some theories predict that quantities like the fine structure constant or the proton-electron mass ratio could drift over cosmological timescales. Astronomers examine the spectra of distant quasars and the abundance patterns in ancient stars for signs of such variation. To date, no convincing evidence of change has been found, but the search itself illuminates the stability of the vacuum. The synergy between theoretical predictions and observational data drives progress in understanding the vacuum. High-resolution simulations of structure formation incorporate dark matter, baryons, and feedback processes to predict the cosmic web. Comparisons with deep surveys test these predictions and refine our models. This dialogue between mathematics and measurement ensures that our ideas remain grounded in reality. On the largest scales, the universe appears remarkably homogeneous and isotropic, yet subtle anomalies have been reported. Features like the hemispherical power asymmetry in the cosmic microwave background, or the alignment of low multipoles, provoke debates about their significance. If confirmed, such anisotropies could hint at early universe physics beyond the simplest inflationary models. They remind us that the vacuum may still harbour secrets at the largest scales. Non-equilibrium processes during reheating and preheating illustrate how far from thermal dynamics can influence cosmology. The particle spectra produced immediately after inflation can be highly non-thermal, affecting the production of dark matter or heavy relics. The subsequent thermalization and chemical equilibration shape the conditions for nucleosynthesis and later phases. Understanding these dynamics requires combining quantum field theory with kinetic theory and numerical simulations. Lepton asymmetry, while closely linked to baryon asymmetry, may have distinct origins and consequences. If the neutrino chemical potentials differ for neutrinos and antineutrinos, this could alter the neutron-to-proton ratio during nucleosynthesis. Observations of primordial helium and deuterium abundances place constraints on such asymmetries. The interplay between lepton and baryon numbers highlights the interconnectedness of the vacuum's properties and cosmic evolution. Modern astronomy is becoming a multi-messenger enterprise. Gravitational waves, high-energy neutrinos, cosmic rays, and electromagnetic signals provide complementary views of energetic events. Detecting these signals from sources like neutron-star mergers allows us to probe extreme densities and magnetic fields and to study matter under conditions that resemble the early universe. Each messenger carries information about how the vacuum responds to different stresses. Emergent gauge fields appear in condensed matter systems, where collective excitations behave as if they are charged under effective forces. In spin liquids, for example, the low-energy excitations can be described by gauge theories similar to those of particle physics. These analogies demonstrate that gauge invariance and fractionalization are not exclusive to high-energy contexts, but can arise from the cooperative behavior of many constituents. They provide laboratory analogues for exploring vacuum concepts like confinement and deconfinement. The study of topological phases of matter has revealed exotic states that are robust against local perturbations. Quantum Hall fluids, topological insulators, and superconductors exhibit edge states and quasi-particles with unusual statistics. These phases are characterized by global properties of their wave functions, rather than local order parameters, echoing the importance of topology in cosmological defects. They hint that the vacuum's organizing principles may be more abstract than previously imagined. Our journey through the quantum universe does not conclude here. It branches into countless directions. The vacuum remains a fertile ground for discovery, with each question opening several more. As experiments push boundaries and theories grow more sophisticated, new vistas of possibility appear. The next chapters will carry us deeper into the interplay between nothingness and existence, where the quiet murmurs of the quantum fields continue to shape the cosmos. As our exploration of the quantum universe gently unfolds, we find ourselves drifting onward from the questions that came before. The themes of emptiness and fullness, the interplay between absence and presence, continue to echo softly in our minds. There is no abrupt conclusion to mark a break, only a quiet progression into deeper waters. The narrative breathes, inviting us to settle into the next chapter of our story with curiosity and calm. It is comforting to imagine the building blocks of reality as little marbles, neat and tangible, occupying definite positions. Yet the deeper we look, the more this image dissolves into a shimmering haze. Quantum field theory teaches that what we call particles are excitations of underlying fields that permeate all of space. In this view, Emptiness is not the absence of substance, but the presence of a vast ocean of fields, quietly humming, waiting to be stirred. Fields are like stretchable fabrics woven through space and time. When energy flows through them, they ripple in discrete units called quanta. In the 1930s, physicists discovered how to quantize these fields, restricting them to oscillate only in certain amounts. Each ripple carries a specific energy, and to observers like us, it appears as a particle. Thus, the marbles of classical intuition give way to the softer metaphor of ripples on a pond. Imagine tossing a pebble into a still lake at twilight. The water responds with concentric waves that travel outward, carrying energy, yet leaving the underlying medium intact. A particle is like that ripple, a temporary expression of a deeper structure, a pattern that emerges when energy disturbs the field. This perspective reveals the vacuum not as emptiness, but as a dynamic medium whose excitations create everything we see. The marbles are gone, replaced by an awareness of patterns and vibrations. This shift in viewpoint invites a more fluid way of thinking about matter. Rather than envisioning tiny objects bumping into one another, we begin to sense a dance of fields that can create, annihilate, and transform ripples. The vacuum is alive with potential, and each particle is a fleeting manifestation of that potential. Even in the absence of obvious excitations, the fields themselves are never truly still. They fluctuate at a quantum level, adding a subtle texture to what we once called nothing. Our journey moves from the concept of individual ripples to the rules that govern their behavior. Symmetry becomes our guide, providing a framework for understanding why certain patterns persist and others vanish. In physics, a symmetry is an operation that leaves the laws of nature unchanged, like rotating a sphere or shifting an experiment in time. Emmy Noether's theorem states that for every continuous symmetry of a system, there is a conserved quantity. This profound connection between symmetry and conservation laws shapes what can emerge from the vacuum. Consider rotating a spinning top. The laws remain the same regardless of its orientation, and the conserved quantity associated with this rotational symmetry is angular momentum. Translational symmetry, moving a system without altering its physics, leads to the conservation of linear momentum and energy. These examples illustrate how symmetries underpin the stability and evolution of particles, dictating the possible ways that fields can ripple and interact. The vacuum itself respects these symmetries unless something profound happens. Noether's insight unifies diverse phenomena under a single principle. When we perceive a persistent feature in nature, like the constancy of energy in a closed system, we can trace it back to a symmetry in the underlying laws. This relationship means that breaking a symmetry can lead to new phenomena by altering the conserved quantities involved. Understanding these patterns will help us grasp how particles can arise and transform in the quantum landscape. Symmetry serves as a compass in our exploration, but it is not absolute. The early universe, hot and dense, was a realm of perfect symmetry where different forces were unified. As the cosmos expanded and cooled, these symmetries spontaneously broke. The vacuum chose specific configurations, like ice crystals forming from water, and the laws of physics, as we know them, emerged. This spontaneous choice created distinct phases of the vacuum, each with its own properties and possibilities. Spontaneous symmetry breaking can be visualized as a ball perched atop a perfectly symmetrical hill. In principle, the ball has no preferred direction, but a small perturbation causes it to roll down toward one side, breaking the symmetry. In the early universe, fields like the Higgs field existed in a symmetric state at high temperatures. As the cosmos cooled, these fields settled into new minima, selecting particular values that gave masses to particles and differentiated the forces. The symmetry was intact in principle, but broken in practice, generating a rich diversity of structures. Phase transitions accompany these symmetry breakings. Just as water transitions from liquid to solid, the vacuum can undergo changes in its structure. The physics literature distinguishes between first-order and second-order cosmological phase transitions. A first-order transition occurs abruptly, like bubbles forming in boiling water, releasing latent heat and leading to a discontinuous change in the order parameter. A second-order transition happens smoothly without latent heat as the system crosses a critical point. Both types are possible in the universe's history, each leaving distinct imprints on cosmic evolution. When a first-order phase transition occurs in the early universe, bubbles of the new phase nucleate within the old phase. These bubbles grow and collide, eventually converting the entire region to the new ground state. The collision of bubbles can produce gravitational waves and other relics. In contrast, a second-order transition involves a gradual change in the state of the vacuum, with no bubbles forming and no latent heat released. In either case, the transition marks a reconfiguration of the vacuum's symmetry, altering the behavior of fields and particles. Spontaneous symmetry breaking implies that the vacuum contains structure even in its lowest energy state. Quantum fields may settle into configurations where some of their components acquire non-zero values. This process determines which particles are massless and which acquire mass. Without such breaking, the world would remain uniform and featureless, with all particles moving at the speed of light. It is the breaking of symmetry that allows complexity to arise from simplicity. One of the most celebrated examples of spontaneous symmetry breaking involves the Higgs field. Proposed in the 1960s, this field permeates all of space and interacts with fundamental particles. At high energies, the Higgs field maintained a symmetric state. As the universe cooled, the field settled into a non-zero value, breaking the symmetry and endowing particles with mass. The discovery of the Higgs boson in 2012 confirmed this mechanism, demonstrating that the vacuum itself plays an active role in shaping the material world. The Higgs mechanism explains why some particles are heavy while others remain light. Particles acquire mass by interacting with the Higgs field. The stronger the interaction, the heavier the particle. Photons, which mediate the electromagnetic force, do not interact with the Higgs field and remain massless, allowing them to travel at the speed of light. This elegant picture turns mass from an intrinsic property into a dynamic relationship with an omnipresent field. The vacuum is not empty, but filled with a background that shapes the inertial resistance of particles. Visualizing the Higgs field as a kind of invisible molasses can help convey its effect. Particles moving through this field experience drag proportional to their coupling strength. Some glide effortlessly, while others slog through and appear heavy. This analogy hints at the richness of the vacuum, an entity that gives weight, sets scales, and determines the behavior of matter. Without the Higgs field, electrons would be massless, atoms would not form, and the universe would be radically different. Mass generation through the Higgs field also underscores how sensitive the cosmos is to the values of underlying parameters. Small variations in the Higgs field's vacuum expectation value could drastically alter the masses of quarks and leptons, the structure of atoms, the rates of nuclear reactions, and the possibility of life all depend on these values. The story of mass is thus the story of a delicate interplay between quantum fields and the vacuum's configuration. The concept of vacuum phases leads naturally to the idea of cosmic phase transitions. In the earliest moments, the universe was a seething plasma of particles and radiation, with symmetries unbroken and forces unified. As the universe expanded, it cooled, and the free energy landscape of fields changed. The ground states of fields shifted, causing new phases to emerge. Each transition altered the interactions between particles and set the stage for subsequent events. Our cosmic history may have included a sequence of such phase transitions. For example, the strong force separated from the electroweak force. The electroweak symmetry broke, and the Higgs field settled into its present value. Each transition likely released energy, creating fluctuations, cosmic relics, or sources of gravitational waves. Understanding these transitions helps us reconstruct the narrative of the early universe. The interplay between temperature, symmetry, and field dynamics guides this rich sequence of changes. Each phase of the vacuum corresponds to a distinct set of physical laws and particle properties. Different phases can support different kinds of excitations, interactions, and forms of matter. The emergence of complexity depends on which phase is selected by the arrangement of fields and the symmetries they respect or break. There may be many vacua, each with its own ground state energy, symmetry pattern, and particle content. The vacuum we inhabit determines the masses of particles, the forces that act between them, and even the possibility of life. This realization transforms nothing into a rich tapestry of potential realities. Throughout our exploration, the vacuum emerges as a creative medium rather than a void. It is a stage for excitations, a repository of symmetries and their breakings, a participant in cosmic events, and a landscape of possibilities. The ripple of a particle, the assignment of mass, the structure of galaxies, and the survival of matter all trace back to the properties of the vacuum. The emptiness between atoms is not empty at all, but alive with fields, fluctuations, and possibilities. Our journey also highlights how intimately connected the smallest and largest scales are. Quantum fluctuations during inflation set the initial conditions for the cosmic web of galaxies and clusters. The symmetry patterns that govern particle interactions echo in the conservation laws that shape star formation and planetary motion. The vacuum's properties, determined at energies far beyond our everyday experience, influence the rhythm of our cosmic environment. In this sense, to understand the universe is to listen to the whispering of the vacuum. As we continue, we might wonder whether new phases of the vacuum await discovery. Perhaps, at energies achievable in future colliders or in astrophysical events, hidden symmetries will reveal themselves. The search for supersymmetry, dark matter, and new particles is partly a search for signs of deeper structures in the vacuum. Observations of cosmic phenomena, such as gravitational waves from phase transitions or signatures of cosmic strings, might provide clues. Each piece of evidence will refine our understanding of what nothing really means. In quantum field theory, the vacuum is a state with the lowest possible energy, yet it is far from trivial. It contains virtual particles flickering in and out of existence, governed by uncertainty principles. These virtual fluctuations contribute to observable phenomena, like the Casimir effect, where two plates in a vacuum attract each other due to changes in the vacuum energy between them. Such effects remind us that the vacuum is a dynamic participant in physics, influencing forces and interactions even in the absence of real particles. The interplay between symmetry and the vacuum shapes the interactions of forces. Gauge symmetries, which underlie the Standard Model, dictate that certain field configurations are physically equivalent. When these symmetries are spontaneously broken, gauge bosons acquire mass and forces become short-ranged. The vacuum expectation values of fields, like the Higgs field, serve as order parameters for these breakings. The patterns of symmetry breaking determine which forces are unified at high energies and how they differentiate as the universe cools. These concepts extend beyond the Standard Model into speculative realms. Grand unified theories propose that the strong, weak, and electromagnetic forces merge into a single force at high energies. The unification requires additional symmetries that break at intermediate scales, producing heavy gauge bosons and predicting phenomena like proton decay. The vacuum plays a crucial role in selecting the unification pattern and determining the masses and couplings of particles. Experimental searches continue to test these ideas. At energies even higher, quantum gravity and string theory attempt to reconcile gravity with quantum mechanics. In string theory, particles are modes of vibrating strings, and the geometry of extra dimensions influences their properties. Different ways of compactifying these dimensions correspond to different vacua, giving rise to the landscape. The vacuum thus connects intimately with geometry and the fabric of space-time. Exploring this connection may reveal how space, time, and matter emerge from a more fundamental framework. Meanwhile, cosmology provides a laboratory for high-energy physics. The early universe attained energies and temperatures that far exceed those achievable on Earth. During inflation and reheating, fields explored regions of the landscape that are inaccessible to current experiments. Observational clues from the cosmic microwave background, large-scale structure, and gravitational waves help constrain models of these epochs. The vacuum of the early universe left imprints that we can still observe today. These imprints include the spectrum of primordial fluctuations, the relative abundances of light elements, and the pattern of anisotropies in the cosmic microwave background. The shape of the fluctuation spectrum points to quantum origins and reveals information about the inflaton potential. The successful predictions of Big Bang nucleosynthesis confirm the conditions of the universe when it was a few minutes old. Together, these observations provide a consistent narrative linking the quantum vacuum to cosmic evolution. Another window into the vacuum comes from laboratory experiments that probe quantum anomalies and phase transitions in condensed matter systems. Superconductors, superfluids, and topological insulators exhibit emergent phenomena where collective excitations behave like particles in quantum field theories. These analogues help us visualize abstract concepts like symmetry breaking, topological defects, and emergent gauge fields. They also suggest that the vacuum might support richer phenomena than previously imagined. In superfluid helium, for example, vortices form when the fluid is rotated. These vortices are quantized, meaning their circulation takes discrete values. The structure of these vortices resembles cosmic strings hypothesized in early universe phase transitions. Studying them provides insights into how such strings might form and evolve. Likewise, experiments with ultra-cold atoms can simulate aspects of quantum fields and gauge theories, revealing how particles emerge from correlated many-body systems. The connection between condensed matter and high-energy physics underscores a unifying principle. The same mathematical structures can describe phenomena across vastly different scales. Concepts like symmetry, topology, and order parameters recur in contexts from superconductors to cosmology. By exploring these analogues, we gain intuition about the abstract vacuum and the dynamics of fields. The unity of physics reveals itself through such cross-disciplinary bridges. Our narrative, while grounded in scientific understanding, also invites reflection on philosophical questions. What does it mean for something to exist? If the vacuum contains fields, fluctuations, and potentialities, is it truly empty? The interplay between absence and presence in quantum theory challenges classical notions of nothingness. Reality emerges not from a void, but from a dynamic background with its own structure and laws. Furthermore, the concept of multiple vacua raises questions about uniqueness and necessity. Are the laws of nature inevitable, or are they environmental accidents within a multiverse? If different bubbles of the landscape realize different physics, our universe becomes one of many possible worlds. This idea shifts the focus from explaining why constants take specific values to understanding the distribution of possible values and the conditions for observers. The vacuum becomes a basis for cosmological diversity. Despite these speculative horizons, our knowledge rests on empirical foundations. Measurements of particle masses, coupling constants, and cosmic background radiation anchor theories to reality. The discovery of the Higgs boson, the precision tests of quantum electrodynamics, and the detection of gravitational waves all confirm aspects of the field-based picture of reality. These successes give confidence that the vacuum and its excitations are genuine aspects of the universe. Looking ahead, experiments such as precision measurements of the cosmic microwave background polarization, searches for primordial gravitational waves, and laboratory studies of CP violation will further illuminate the vacuum. Future colliders may probe the Higgs potential more precisely, looking for signs of additional fields or phase transitions. Observatories may detect gravitational waves from early universe events, providing a direct glimpse into the dynamics of symmetry breaking and reheating. Each discovery will refine our understanding of the vacuum's role in cosmic history. The narrative of particles as ripples riding quantum fields invites us to reimagine the nature of reality. The vacuum, far from being an inert backdrop, is an active participant that shapes the existence of particles, the strength of forces, and the evolution of the cosmos. Symmetry and its breaking guide the emergence of structure, connecting deep principles to observable phenomena. Inflation stretches quantum whispers into cosmic patterns, linking the smallest scales to the largest. Reheating and symmetry, breaking, usher in the familiar world of matter, while a slight imbalance ensures our existence. As we finish this segment of our journey, the story remains open. The vacuum still holds secrets, unknown fields, hidden symmetries, and perhaps other phases we have yet to encounter. The landscape of possibilities is vast, and our path through it is guided by curiosity, observation, and imagination. In the next part of our exploration, we will continue to wander through this quantum terrain, seeking deeper understanding without rushing to a final conclusion. The calm, mysterious rhythm of the narrative will carry us forward, inviting us to listen to the whispers of the quantum universe. At first glance, the duality of waves and particles may seem perplexing, yet this subtlety lies at the heart of quantum fields. Fields can be thought of as continuous oscillators that support discrete quanta, and each excitation behaves as both a wave and a particle. This dual character is why electrons can form interference patterns when we do not observe them, yet appear as localized hits on a detector when measured. The vacuum acts as a canvas where these probabilistic ripples propagate, interfering and blending until observation forces a particular outcome. Even when there are no obvious excitations, the vacuum is never still. Quantum uncertainty requires that the fields cannot have exactly zero energy, leading to a background of zero-point fluctuations. These fluctuations contribute to observable effects, such as the Casimir force between closely spaced plates, where the vacuum energy pushes them together. In cosmology, the cumulative energy of vacuum fluctuations may play a role in the observed dark energy, hinting that the emptiness we imagine is actually restless. Entanglement adds another layer of subtlety to the picture of fields and particles. When two excitations arise from a common source, their properties become correlated in ways that persist even across cosmic distances. A measurement on one immediately constrains the possible outcomes for the other, showing that information about quantum states can be delocalized across the vacuum. This phenomenon illustrates that the vacuum is not just a collection of independent points, but a web of relationships that spans space and time. The act of measurement itself entangles the observer with the system, effectively slicing through the coherent ripples and selecting a definite outcome. In the process, known as decoherence, the environment, including the ever-present vacuum, records information about the system, causing interference patterns to fade away. What appears as the collapse of a wave function is a consequence of this interaction with a vast background of degrees of freedom. Such considerations remind us that the vacuum participates in every event, quietly mediating between possibility and actuality. Different observers can disagree on whether the vacuum contains particles, emphasizing that particles are observer-dependent concepts. An accelerating observer perceives a warm bath of particles, even when an inertial observer sees empty space, an effect known as the Unruh phenomenon. Near the horizon of a black hole, an outside observer detects Hawking radiation emitted from what appears to be vacuum, showing how geometry and motion shape the quantum state. These insights underscore that the notion of emptiness is not absolute, but relative to the observer's trajectory and the space-time background. To make sense of the diverse phenomena emerging from quantum fields, physicists use the language of symmetries. Symmetries are operations that leave the equations of motion invariant, and they are associated with groups like the rotations in 3 dimensions or the translations in spacetime. Particles are classified according to how they transform under these groups, with spin reflecting rotational symmetry and momentum corresponding to translational symmetry. The Poincare group, which combines rotations and translations, underpins the classification of all fundamental particles in our flat spacetime. In addition to spacetime symmetries, there are internal symmetries that relate different types of particles. The standard model is built on gauge symmetries described by the groups SU of 3, SU of 2, and U of 1, corresponding to the strong, weak, and electromagnetic forces. Gauge invariance requires that certain transformations can be performed independently at each point in space and time, introducing gauge bosons that mediate interactions. These symmetries are not arbitrary. They dictate the possible forms of interactions and ensure that the theory is consistent and renormalizable. When symmetries of the classical theory are violated by quantum effects, the result is known as an anomaly. Anomalies can have profound implications, such as the non-conservation of certain currents or the breaking of expected symmetries at the quantum level. In a consistent gauge theory, anomalies must cancel to avoid mathematical inconsistency, constraining the possible combinations of particles. The interplay between anomalies and symmetries provides a deep connection between quantum consistency and the spectrum of matter. A continuous symmetry that is spontaneously broken gives rise to massless excitations called Goldstone bosons. These modes correspond to ripples along the valley of degenerate minima in the potential, reflecting the broken symmetry. In a gauge theory, these would-be Goldstone bosons are eaten by gauge bosons, giving them mass via the Higgs mechanism. The existence of such massless modes in other contexts, like condensed matter systems, offers an analogue for understanding how breaking symmetries can lead to emergent phenomena. While many symmetries are exact, others are approximate or discrete. Parity, charge conjugation, and time reversal symmetries encapsulate reflections of space, exchange of particles with antiparticles, and reversal of motion. Experiments have revealed that certain combinations, such as CP symmetry, are not perfectly conserved, providing one of the necessary ingredients for explaining the dominance of matter over antimatter. Understanding the subtle ways in which these symmetries are broken remains a frontier in physics and connects microscopic laws to cosmic history. At extremely high temperatures, the energy landscape of fields is symmetric. But as the universe cools, the potential may develop multiple minima. The field configuration then chooses one of these minima, breaking the symmetry and establishing a new phase. This process is analogous to a magnet cooling and aligning its spins, selecting a direction despite the rotational symmetry of the equations. Each region of space may choose a different orientation, leading to domains separated by boundaries, where the field interpolates between phases. The nature of a phase transition depends on how abruptly the system crosses from one state to another. In a first-order transition, regions of the new phase nucleate as bubbles within the old phase, and their expansion and collisions release latent heat. Such violent dynamics can generate gravitational waves that might be detectable with future observatories. In a second-order transition, the change is continuous and no latent heat is released. But fluctuations grow large and the correlation length diverges, leaving critical imprints on the system. When symmetry breaking occurs, topological defects can form if the field configuration cannot be smoothly deformed into the trivial state. Domain walls appear at boundaries between different vacuum choices. Cosmic strings arise when a phase transition leaves a vortex-like configuration, and monopoles emerge when the field wraps around a sphere. These defects carry energy and can influence cosmic evolution, acting as seeds for structure or sources of radiation. Their potential presence motivates searches for signatures in the cosmic microwave background and astrophysical observations. Cosmic phase transitions thus provide a way to connect microphysics with macroscopic phenomena. The growth of domains, the formation of defects, and the release of latent heat can all leave relics that survive to the present day. Gravitational waves from bubble collisions, deviations in the abundances of light elements, or the presence of relic particles could be evidence of events that occurred fractions of a second after the Big Bang. By studying these relics, we attempt to reconstruct the timeline of the early universe and the choices made by the vacuum. The Higgs mechanism is a striking example of spontaneous symmetry breaking applied to gauge theories. In the electroweak sector, a complex scalar field with 4 real components acquires a non-zero vacuum expectation value, breaking the SU 2 times U1 symmetry down to the electromagnetic U1. 3 of the field's components become the longitudinal modes of the W and Z bosons, giving them mass, while the 4th manifests as the Higgs boson. This process shows that masses of gauge bosons arise not from explicit breaking, but from the vacuum choosing a particular orientation in field space. Fermions obtain mass through their couplings to the Higgs field via interactions known as Yukawa couplings. Each type of quark and lepton couples with its own strength, meaning that the more strongly a fermion interacts with the Higgs, the heavier it becomes. The pattern of these couplings spans many orders of magnitude, from the tiny value giving the electron its mass to the much larger value associated with the top quark. The origin of this pattern remains one of the deep puzzles of particle physics, pointing to structure beyond the standard model. The shape of the Higgs potential is often depicted as a Mexican hat, with a ring of minima encircling a central maximum. At high energies, thermal fluctuations push the Higgs field to the symmetric point at the top of the hat. But as the universe cools, the field falls into one of the valleys, selecting a specific value. The curvature of the potential at the minimum determines the Higgs boson's mass, while the height and width of the potential set the scale for electroweak symmetry breaking. Measuring these parameters provides clues about whether the Higgs sector is alone or part of a richer landscape. Quantum corrections can modify the Higgs potential, raising the possibility that our vacuum is only metastable. Calculations suggest that the current values of the Higgs mass and the top quark mass place us near a boundary between stability and instability. If the potential dips below zero at very high energies, quantum tunneling could someday cause the field to roll into a deeper minimum, radically altering the universe. While the lifetime of our vacuum seems enormous, the mere existence of this possibility illustrates how the vacuum's properties remain an active area of research. The delicate smallness of the Higgs mass relative to the Planck scale raises the problem of naturalness. Quantum fluctuations tend to drive the Higgs mass toward the highest energy scales, requiring fine-tuning to maintain its observed value. Supersymmetry, composite Higgs models, and extra dimensions have been proposed to address this problem by introducing new symmetries or dynamics that stabilize the Higgs mass. Experiments at colliders and in cosmic observations continue to search for signs of these mechanisms, as they would reveal a deeper structure underlying the vacuum. During the first microseconds after the Big Bang, quarks and gluons roamed freely in a hot plasma. As the universe cooled below 1 trillion degrees, these constituents became confined into protons, neutrons, and other hadrons, an event known as the quark-hadron transition. Experiments with heavy ion collisions recreate this quark-gluon plasma, providing insights into the behavior of matter under extreme conditions. The relics of this transition influenced the abundances of particles that later formed nuclei and atoms, connecting the microphysics of the strong force to the composition of the cosmos. A bit later, at energies around 100 billion degrees, the electroweak force separated into the electromagnetic and weak forces. Above this temperature, the Higgs field's expectation value vanished, and the W and Z bosons were massless, making the weak force as strong as electromagnetism. When the universe cooled below this critical temperature, the Higgs field acquired its non-zero value, breaking the symmetry and giving mass to the W and Z bosons. Whether this electroweak phase transition was first order or second order has implications for baryogenesis and gravitational wave signals. Neutrinos, elusive particles that interact only via the weak force, decoupled from the thermal plasma when the universe was about 1 second old. From that point forward, neutrinos free-streamed through space, forming a cosmic neutrino background analogous to the cosmic microwave background. Their energy density influenced the expansion rate during nucleosynthesis and affected the growth of structure. Although these relic neutrinos are difficult to detect directly, their existence is inferred from the successful predictions of light element abundances. A few minutes after the Big Bang, protons and neutrons fused to form the first light elements in a process known as Big Bang nucleosynthesis. The relative abundances of hydrogen, helium, and traces of deuterium and lithium depend on the density of baryons and the expansion rate. Observations of primordial element ratios provide strong support for the hot Big Bang model and constrain the number of light particle species, including neutrinos. This era demonstrates how sensitive cosmic evolution is to the vacuum's content and the constants of nature. As the universe continued to cool, hypothetical dark matter particles fell out of thermal equilibrium. Their relic abundance depends on their interaction cross-sections, which determine how quickly they annihilate. Weakly interacting massive particles, one popular candidate, would freeze out with a density compatible with observations if their interactions are of electroweak strength. Alternative scenarios involve axions, sterile neutrinos, or other exotic particles, each with its own freeze-out or production mechanism. These particles remain undiscovered, and their existence would reveal new facets of the vacuum. The standard Big Bang model raises the horizon problem. Distant regions of the cosmic microwave background have nearly identical temperatures despite never being in causal contact. Cosmic inflation resolves this by positing that a tiny region was stretched exponentially to encompass the observable universe, allowing thermal equilibrium before inflation. Without this accelerated expansion, the homogeneous and isotropic cosmos would be difficult to explain. The horizon problem illustrates how global properties of the universe can hinge on events in a fraction of a second. Another cosmological puzzle is the flatness problem. The spatial curvature of the universe evolves with time, and for it to remain close to zero today, it must have been fine-tuned to extraordinary precision at early times. Inflation dilutes any initial curvature, driving the universe toward flatness by increasing its size by many orders of magnitude. Observations of the cosmic microwave background and large-scale structure indicate that the universe is indeed nearly flat, consistent with inflationary predictions. This flattening effect is a natural consequence of the rapid expansion. For inflation to last long enough, the field driving it must satisfy slow roll conditions, meaning its potential must be sufficiently flat and its motion sufficiently gentle. These conditions allow the field to dominate the energy density and cause an almost constant vacuum energy. Many models propose different potential shapes, from simple monomials to plateau-like forms inspired by string theory. The details of the potential influence the spectrum of primordial fluctuations and the predicted amplitude of gravitational waves, making cosmological observations a window into high-energy physics. Quantum fluctuations during inflation are stretched to macroscopic scales, providing the seeds for all cosmic structure. As each patch of space exits the horizon, its quantum state freezes into a classical perturbation. The spectrum of these perturbations is nearly scale invariant, with slight deviations that depend on the shape of the inflaton potential. These variations in density eventually grow under gravity to form galaxies, clusters, and voids. Without the amplification of quantum jitters by inflation, the universe would be smooth and featureless. Inflation also predicts a background of primordial gravitational waves arising from the stretching of spacetime itself. These tensor modes imprint a distinct pattern of polarization in the cosmic microwave background known as B modes. Detecting this signature would provide strong evidence for inflation and measure its energy scale. So far, observations have placed upper limits on the amplitude of these waves, constraining models of inflation. Future experiments aim to reach sensitivities capable of detecting or further restricting this elusive signal. After inflation and reheating, tiny density contrasts began to grow under the influence of gravity. In regions slightly denser than average, matter pulled in more material, while underdense regions gave up matter, leading to the formation of a cosmic web. Dark matter played a crucial role, as its gravitational influence guided the collapse without being hindered by radiation pressure. Over billions of years, these inhomogeneities evolved into galaxies, clusters, and the filamentary structure observed today. The relationship between initial fluctuations and the large-scale structure reveals the history of the universe. The cosmic microwave background provides a snapshot of the universe when it was only 380,000 years old. Small temperature variations reflect the density fluctuations seeded during inflation and modified by interactions between photons and baryons. Precision measurements of these anisotropies have enabled determination of cosmological parameters with remarkable accuracy. They also confirm the predictions of a nearly scale-invariant fluctuation spectrum and the presence of acoustic peaks corresponding to sound waves in the primordial plasma. Such observations continue to test models of the early universe. Baryon acoustic oscillations are a fossil record of these primordial sound waves. As the universe expanded, the oscillations ceased, leaving a characteristic scale imprinted in the distribution of galaxies. By measuring this scale at different redshifts, astronomers map the expansion history and the influence of dark energy. The agreement between baryon acoustic oscillation measurements and cosmic microwave background data strengthens the standard cosmological model and provides constraints on possible deviations. This harmony across epochs underscores the coherence of our cosmic story. The distribution of matter on large scales forms a vast cosmic web, with filaments connecting dense clusters and large voids in between. Numerical simulations show that this pattern arises naturally from the growth of initial fluctuations and the gravitational interplay of dark matter and baryons. Observations through galaxy surveys and gravitational lensing reveal the filamentary network and help determine the composition of the universe. Exploring the cosmic web offers insights into how the vacuum's properties and the initial conditions combine to shape the visible universe. When inflation ended, the universe was cold and empty of ordinary particles, with its energy stored in the coherent oscillations of the inflaton field. Reheating transformed this vacuum-like state into a hot plasma by transferring energy into particles. The details of this transfer depend on the couplings of the inflaton to other fields and may involve direct decays or more explosive phenomena. Although reheating is crucial for connecting inflation to the subsequent hot Big Bang, its precise dynamics remain uncertain. One mechanism for reheating is preheating, where the oscillating inflaton transfers energy to other fields through parametric resonance. In this process, certain modes of the coupled fields grow exponentially, quickly converting a significant fraction of the inflaton's energy into particle excitations. The resulting particle spectrum can be far from equilibrium and may lead to non-thermal processes. Preheating illustrates how the vacuum can undergo rapid transitions, filling space with new particles in a fraction of a second. Following the initial burst of particle production, interactions among the produced quanta lead to thermalization. Scatterings and decays redistribute energy and bring the plasma into a near-thermal state characterized by a temperature. The temperature at the end of reheating sets the initial conditions for Big Bang nucleosynthesis and influences the production of relic particles such as dark matter. The efficiency and timescale of thermalization thus link the microphysics of reheating to the observable universe. Reheating may also generate heavy, unstable particles that play roles in baryogenesis or dark matter creation. If the inflaton couples to fields that decay asymmetrically or produce long-lived remnants, these processes can imprint new features on the cosmic inventory. The interplay between reheating, particle production, and fundamental symmetries remains an active area of theoretical exploration. By connecting the end of inflation to later cosmic history, reheating bridges the gap between vacuum-dominated expansion and matter-dominated evolution. The dominance of matter over antimatter in the universe requires processes that violate baryon number, violate charge and parity symmetries, and occur out of thermal equilibrium. These three criteria, known as the Sakharov conditions, provide a blueprint for baryogenesis. Various proposed mechanisms operate at different energy scales, from the grand unification era to the electroweak scale. Exploring how these conditions are satisfied in nature helps explain why we find ourselves in a matter-rich universe, and not a symmetric mixture of particles and antiparticles. In the Standard Model, CP violation occurs in the weak interactions of quarks, but the amount of violation is too small to account for the observed asymmetry. This suggests that additional sources of CP violation exist beyond the Standard Model, perhaps in the neutrino sector, or in interactions involving new particles. Experiments measuring neutrino oscillations and rare meson decays seek to quantify CP violation with greater precision. Uncovering new sources of CP violation would shed light on the origin of the matter-antimatter imbalance. Electroweak baryogenesis posits that the asymmetry was generated during the electroweak phase transition. For this mechanism to work, the transition must be strongly first-order, allowing bubbles of the broken phase to expand and create out-of-equilibrium conditions. Sphaleron processes inside the bubble walls can then convert CP violating interactions into a net baryon number. However, the Standard Model's Higgs sector does not provide a sufficiently strong first-order transition, motivating extensions with additional scalar fields or new interactions. Leptogenesis offers another avenue for producing the baryon asymmetry. Heavy right-handed neutrinos, which naturally arise in seesaw models of neutrino mass, decay in a CP violating manner, generating an excess of leptons over antileptons. Non-perturbative electroweak processes, known as sphalerons, partially convert this lepton asymmetry into a baryon asymmetry. The link between leptogenesis and neutrino masses means that measurements of neutrino properties could indirectly inform our understanding of the cosmic matter excess. Although the Big Bang should have produced equal amounts of matter and antimatter, our universe is overwhelmingly composed of matter. When particles meet their antiparticles, they annihilate, releasing pure energy. So any slight imbalance would determine the leftover matter. The early universe buzzed with pair creation and annihilation, but an unknown mechanism tilted the balance, leaving more matter than antimatter. Understanding this bias is crucial to explaining why anything exists at all, and experiments continue to probe possible origins of the asymmetry. The concept of the string theory landscape arises from the multitude of ways string theory's extra dimensions and fluxes can be arranged. Each configuration yields a different vacuum with its own low-energy physics, leading to an immense number of possibilities. Estimates suggest that there could be on the order of 10 to the power of 500 distinct vacua, each corresponding to a different set of particle masses, coupling constants, and cosmological constants. This vast multiplicity challenges the notion that the fundamental laws are uniquely determined. Within this landscape, the anthropic principle suggests that observers can only exist in vacua where conditions allow for complex structures. This idea posits that our universe appears fine-tuned, not because the constants are uniquely determined, but because only those vacua with suitable values can harbour life. While the existence of many metastable vacua is widely accepted, applying anthropic reasoning to explain physical parameters remains controversial. Nevertheless, It offers a framework for thinking about why certain features of the vacuum take the values we observe. Vacua can be metastable, meaning the field resides in a local but not global minimum of its potential. Quantum tunneling can allow transitions to a lower energy vacuum, creating a bubble of the new phase that expands at nearly the speed of light. Inside the bubble, the laws of physics may differ, with different particle masses or force strengths. Whether our vacuum is truly stable or metastable is an open question, and the existence of such transitions would have dramatic implications for the fate of the universe. Another facet of the vacuum is its energy density, which appears as the cosmological constant, or dark energy, in Einstein's equations. Observations indicate that this vacuum energy drives the accelerated expansion of the universe, yet its magnitude is puzzlingly small compared to theoretical expectations. Quantum field theory predicts contributions from zero-point energies that are many orders of magnitude larger, leading to the cosmological constant problem. Resolving this discrepancy may require new insights into the relationship between quantum fields, gravity, and the structure of the vacuum. In some models, inflation does not end everywhere simultaneously, but continues eternally in some regions, producing an ever-growing multiverse. Each region that exits inflation forms a bubble universe with its own vacuum, while inflation continues elsewhere. This eternal inflation amplifies the importance of the landscape, as different bubbles can realize different vacua. The measure problem: how to assign probabilities to different vacua in an infinite multiverse, remains an unresolved issue in cosmology and challenges our understanding of prediction and explanation. Collisions between bubbles of different vacua in an eternally inflating multiverse could leave observable signatures. If another bubble collided with ours in the past, it might produce temperature anisotropies, or disk-like features in the cosmic microwave background. Searches for such signatures so far have not revealed conclusive evidence, but future surveys could improve sensitivity. Gravitational waves from vacuum decay events or bubble collisions offer another possible probe, linking the physics of the multiverse to observable phenomena. The idea of scanning fundamental constants across the landscape implies that parameters, like the fine structure constant or the Higgs vacuum expectation value, can vary from one vacuum to another. Some values might allow for stable atoms and chemistry, while others would not. The existence of a multitude of vacua with differing constants thus provides a natural context for anthropic selection. Yet it also raises profound questions about whether the laws of physics are fundamental or contingent, shaped by the geography of the vacuum landscape. Probing the many faces of nothing involves both theoretical investigations and experimental searches. High-energy colliders may reveal new particles or interactions that hint at additional fields or symmetries. Precision cosmology, including measurements of the cosmic microwave background, large-scale structure, and gravitational waves, can test models of phase transitions, inflation, and vacuum decay. The interplay between string theory, quantum field theory, and observational data continues to refine our understanding of vacua. As our exploration advances, each new clue helps map the vast terrain of possible realities. Entanglement also appears in places we seldom consider. Photons emitted by the sun can become entangled with vibrations in the solar plasma. Electrons emitted in radioactive decay share correlations across astronomical distances. Even the light from a candle may carry subtle entanglements between its color and direction. These examples remind us that quantum connections are not confined to the laboratory. They permeate the cosmos and highlight the relational fabric of nature. The study of multipartite entanglement reveals an even richer tapestry. Instead of two particles sharing a simple correlation, entire groups can be entangled in ways that have no classical analog. Greenberger-Horn-Zeilinger states exhibit perfect correlations among 3 or more qubits. Cluster states form the backbone of measurement-based quantum computing, where computation proceeds by making sequential measurements on a highly entangled resource. Through entanglement swapping, 2 particles that never interacted directly can become entangled via intermediate partners, showing how entanglement can be woven and rewoven across systems. Entanglement is not just a curiosity, it is a resource that can be quantified and consumed. In quantum thermodynamics, entanglement contributes to the extractable work from a system. A pair of entangled particles has a lower entropy than 2 separate particles in mixed states, and this difference can be harnessed. Concepts like entanglement entropy and negativity provide measures of the depth of quantum correlations. As we build quantum devices, we must learn to manage entanglement like any other resource, storing, distributing, and converting it as needed for computation and communication. Protocols such as quantum teleportation and superdense coding demonstrate the practical power of entanglement. In teleportation, a quantum state is destroyed at one location and reconstructed at another by consuming a shared entangled pair and sending classical bits. In superdense coding, 2 classical bits of information are transmitted by sending a single qubit that is entangled with another. Quantum key distribution uses entangled photons to create shared random strings. Any eavesdropper disturbs the entanglement and is detected. These techniques highlight how entanglement can be converted into communication capacity and security. Entanglement also obeys limits. It cannot be freely shared among many partners. This is known as the monogamy of entanglement. If 2 qubits are maximally entangled, they cannot be equally entangled with a third. This restriction is unlike classical correlations, which can be broadcast. The monogamy of entanglement underpins the security of quantum cryptographic protocols and shapes the structure of many body quantum states. Bell-type experiments continue to push boundaries. In some tests, measurement settings are chosen by cosmic signals, such as light from distant quasars, if hidden variables existed that conspired with the experimenter's choices. They would need to have coordinated with stars billions of years ago. Other tests use human participants to generate random bits, closing the so-called freedom of choice loophole. These creative experiments reinforce the conclusion that the correlations observed cannot be explained by any local hidden variables and strengthen our confidence in the non-classical nature of the world. The Clauser-Horn-Shimony-Holt (CHSH) inequality is a simple form of Bell's inequality that can be violated by quantum mechanics. It involves measuring correlations between 2 entangled particles using different detector settings. Classical local theories impose an upper bound on the sum of these correlations. Quantum mechanics predicts a larger value, which experiments have consistently observed. The CHSH inequality has become a benchmark for testing entanglement and is used in certifying random number generators that rely on quantum unpredictability. Philosophically, the EPR paradox and Bell's theorem raise questions about realism and locality. Realism suggests that physical properties exist independently of measurement, while locality insists that influences travel no faster than light. The violation of Bell's inequalities shows that we cannot maintain both assumptions simultaneously. Many interpretations of quantum mechanics relax realism, accepting that properties like spin and polarization are not determined until measured. Others adopt a non-local perspective, positing that entangled particles influence one another instantaneously in a way that preserves the overall structure of the theory. Some speculative approaches link entanglement to the geometry of spacetime itself. In certain models of quantum gravity, space may emerge from networks of entangled qubits, The holographic principle suggests that the information within a volume is encoded on its boundary, and entanglement plays a role in knitting together the fabric of space. Though these ideas remain on the frontier of physics, they hint that entanglement might be more than a property of matter. It could be a building block of spacetime. The classical bit, realized in a transistor or magnetic domain, embodies definite states that can be copied and measured without disturbance. Bits underpin our current digital world, enabling the stable storage and transmission of information. As we shrink devices and approach quantum scales, classical bits face limits due to thermal fluctuations and quantum tunneling. The qubit offers a new paradigm, but it demands an understanding of coherence, entanglement, and measurement that goes beyond classical intuition. Physical implementations of qubits vary widely. Trapped ions use electric fields to confine charged atoms and manipulate their internal energy levels with lasers. Superconducting circuits harness the collective motion of millions of electrons acting as a single quantum object. Photons traveling through optical fibers encode information in polarization or time bins. Each technology balances trade-offs between coherence time, gate speed, and scalability. The diversity of platforms shows that qubits are not tied to any particular substance. They are patterns of excitation that we engineer and control. Quantum information cannot be cloned, a result known as the no-cloning theorem. If we could copy an unknown qubit perfectly, we could create multiple identical copies and measure them to determine the state without disturbance. This would violate the uncertainty principle and allow tasks forbidden by quantum mechanics. The no-cloning theorem is a direct consequence of the linearity of quantum evolution. While classical bits can be duplicated freely, qubits require error correction codes that spread information across multiple physical systems to detect and correct errors without directly copying the state. The recognition that erasing information costs energy spurred interest in reversible computing. By designing logic gates that run backward as well as forward, one can perform computations while minimizing heat dissipation. Reversible computing has not yet become mainstream, but it offers a path to more energy-efficient processors. At the quantum level, all fundamental operations are unitary and reversible, reflecting the deterministic evolution of the wave function. Irreversibility enters only when information is discarded, or when we measure and coarse-grain the system. Maxwell's demon remains a touchstone for discussions of entropy. Modern experiments implement the demon's strategy in single electron boxes and optical cavities, verifying that the demon's memory must be reset and that the cost matches Landauer's bound. These experiments show that the second law of thermodynamics survives intact when information is accounted for. They also illustrate that information has physical significance, bridging the gap between abstract logic and concrete energy. Decoherence can be thought of as the leakage of phase information into degrees of freedom we do not monitor. A quantum system interacts with an environment that is too large to keep track of. The environment picks up which path information about the system, and interference between paths disappears. From our perspective, the system appears to have jumped into a definite state, but in reality, the global wave function includes all possibilities, each correlated with a different environmental record. Decoherence is therefore a statement about our limited access to the environment and the effective classicality that results. The measurement problem has given rise to various interpretations of quantum mechanics. The Copenhagen interpretation holds that the wave function collapses randomly when measured, an axiom outside the formalism. The many worlds interpretation posits that all branches persist and decoherence prevents interference between them. Objective collapse models introduce new dynamics that trigger collapse spontaneously or when mass is large. Relational interpretations suggest that states are relative to observers. Though these views differ on ontology, they agree on the empirical predictions and underline that measurement and information are at the heart of the theory. Pointer states vary depending on the system and its environment. In a cavity quantum electrodynamics experiment, the photon number states can act as pointer states because they leave imprints on atoms passing through the cavity. In a spin ensemble immersed in a magnetic field, the collective spin orientation may be stable because environmental noise couples to that observable. The identification of pointer states is not fixed by the formalism. It emerges from the details of the interaction Hamiltonian. By engineering environments with tailored interactions, one can select different pointer bases and thus control which properties remain classical. Einselection, short for environment-induced superselection, is the process by which certain states are dynamically selected because they are robust against decoherence. These pointer states persist while other superpositions rapidly decay. For example, the position of a dust particle floating in a beam of sunlight is einselected because photons scattering off the dust carry away which path information, causing superpositions of different positions to collapse into a mixture. The dust particle does not have an inherent classical position. It becomes classical because the environment monitors its position and copies that information widely. Information about pointer states spreads redundantly into the environment, enabling multiple observers to agree on the outcome of a measurement. When you look at a tree, you are not directly touching it. You are intercepting photons that have scattered off its leaves. Someone else looking from a different angle intercepts a different set of photons. If the tree were in a superposition of positions, these photons would carry conflicting information, making it impossible for both observers to see the same tree. Decoherence and einselection ensure that the environment records only one pointer state, and quantum Darwinism asserts that this state is replicated many times over. The redundancy of records explains why the classical world appears objective. A single photon scattering off a dust grain carries only a tiny bit of information. But when trillions of photons scatter, each carrying a bit, the position of the dust grain becomes imprinted millions of times over. Researchers have calculated that a micrometer-sized dust particle in sunlight acquires redundant position information after only a microsecond. This redundancy means that different observers looking at different parts of the environment will agree on the particle's location. Objective reality emerges because the same story is told repeatedly across many fragments of the environment. Time's arrow and entropy are intertwined with information. Entropy measures the number of ways a macrostate can be realized by microstates. Low entropy states have few microstates and are unlikely. High entropy states have many microstates and are typical. The second law of thermodynamics tells us that, in an isolated system, entropy tends to increase. But this law is statistical, not absolute. It arises because low entropy states are rare and high entropy states are common. When we observe a system and find it in a low entropy state, we must consider how it arrived there and how it will evolve in the presence of fluctuations and interactions. In the context of quantum mechanics, entropy and information are deeply connected. Von Neumann entropy quantifies the uncertainty associated with a quantum state. Pure states have zero entropy, while mixed states have positive entropy. When a system is entangled with its environment, the system alone is in a mixed state, and its entropy reflects our lack of knowledge about the global pure state. Erasing information about a system requires discarding correlations, and thereby increases entropy. Time's arrow, in this picture, is a statement about the accumulation of entanglement and the growth of inaccessible information. The arrow of time also has a psychological aspect. We remember the past because of the existence of records. We do not remember the future because information about the future does not yet exist. The growth of entropy and the growth of accessible records march hand in hand. This perspective invites us to think of time as emergent from correlations. When two systems interact and entangle, they build correlations that can serve as a memory. A clock ticks by, leaving a record of its state in its environment. Thermodynamic time arises because forward processes create correlations more readily than reverse processes. Quantum thermodynamics explores these ideas in controlled settings. In small systems, fluctuations can momentarily decrease entropy, but on average, the second law holds. The Jarzynski equality relates the work done on a system during a non-equilibrium process to the free energy difference. Experiments with single atoms and trapped ions have verified these relations. They show that one can extract work by using information about fluctuations, but the cost of acquiring and erasing that information must be included. In this domain, the boundaries between work, heat, and information blur. Recent experiments implement Maxwell's demon with a single electron or an optical cavity. The demon observes the state of a particle and applies a feedback protocol to extract work. For instance, by measuring whether an electron is in a high or low energy state, and then lowering a barrier accordingly, one can extract energy on average. However, the measurement device must reset its memory, dissipating energy in the process. These experiments confirm that the energy extracted never exceeds the cost of information processing. They provide a tangible link between information theory and thermodynamics. Macroscopic superpositions challenge our sense of reality. Schrödinger's famous cat, trapped in a box with a quantum trigger, illustrates the absurdity of applying quantum superposition to everyday objects. In practice, no one has ever observed a cat in a superposition of alive and dead. But researchers have created superpositions of large molecules, tiny cantilevers, and superconducting circuits. In these experiments, the systems behave like quantum waves, interfering with themselves. The interference patterns vanish when the environment monitors the system. The larger the system, the harder it is to keep the environment at bay, so the superposition collapses quickly. One striking example uses molecules composed of hundreds of atoms. These molecules are heated in an oven, cooled, and then sent through a diffraction grating. They spread out like waves, producing an interference pattern on a distant screen. If the molecules collide with even a single air molecule, the pattern disappears. In another experiment, a small vibrating beam is cooled to its ground state and then driven into a superposition of vibrational states. Laser pulses allow the beam to interfere with itself, showing quantum behavior. Such experiments bring quantum weirdness into the realm of the visible. Superconducting circuits can also be put into macroscopic superpositions. In a flux qubit, millions of electrons move collectively around a ring. The current can flow clockwise, counterclockwise, or in a superposition of both. By coupling such qubits to resonators and manipulating them with microwave pulses, researchers create complex entangled states. These devices are the building blocks of quantum processors. The fact that such large aggregates of electrons can maintain coherence for microseconds is remarkable, and is a testament to the careful engineering that isolates them from noise. Understanding emergence as a pattern requires shifting from substance to relation. In the classical view, objects have intrinsic properties that exist independently. In the quantum view, properties arise from interactions and entanglements. A chair is solid because its atoms share coherent patterns that resist deformation. A tree is alive because its molecules participate in cycles of energy and information that sustain its structure. Each emergent level is a story told by patterns of information that persist through time. These stories are not illusory. They are real features of the world that arise from the underlying quantum fabric. Coarse graining is a mathematical technique that helps us describe emergence. Instead of tracking each particle's position and momentum, we group large numbers of particles into effective variables like density, pressure, and temperature. These macroscopic variables obey equations that do not reference microscopic details. The success of fluid dynamics, thermodynamics, and elasticity theory shows that emergent descriptions can be accurate and predictive. Similarly, in quantum mechanics, decoherence and redundancy allow us to ignore most of the microscopic details and focus on stable pointer states. Emergence is the art of finding the right collective variables to describe patterns. Renormalization is another powerful concept illustrating emergence. In physics, renormalization involves systematically averaging over high-frequency fluctuations to derive effective theories at lower energies. The behavior of a magnet near its critical point, the flow of electrons in a metal, and the geometry of spacetime in some approaches to quantum gravity all involve renormalization. The idea is that many details at small scales wash out, leaving behind a few relevant parameters. Similarly, the classical world emerges because most quantum details wash out, leaving behind stable patterns. The renormalization group teaches us that laws can change with scale, and the laws governing everyday objects need not resemble the laws at the smallest scales. The phrase "it from bit" captures the idea that what we consider the physical world arises from information. Originally coined by John Archibald Wheeler, it suggests that the fundamental building blocks are bits or qubits, and that reality is a vast information processing network. Modern quantum information theory gives mathematical substance to this idea. Entanglement entropy measures how much information is shared between parts of a system. The holographic principle in theoretical physics proposes that the information content of a region of space is proportional to the area of its boundary. Such ideas hint that space, time, and matter may emerge from more fundamental informational structures. Emergence is not a one-way street. Higher-level structures can influence lower-level dynamics. In biology, genes encode proteins, which create cells, which build organisms. These organisms interact with their environments, shaping evolutionary pressures that feed back to gene frequencies. In quantum systems, classical control devices shape the evolution of qubits, which in turn alter the devices. This interplay of levels is called downward causation. It reminds us that our narratives about emergence are part of the pattern too. We are both observers of and participants in the story, our understanding shaping the world we inhabit. As our exploration deepens, we may ask whether the classical world is inevitable or contingent. Could there be universes where decoherence proceeds differently, where pointer states are distinct, where information flows along other channels? Such questions border on speculation, but they highlight the role of environmental conditions in shaping the emergent world. The constants of nature, the density of matter, the spectrum of radiation, all influence which patterns survive. In our universe, the conditions allow atoms, molecules, stars, and life to form. The classical reality we experience is one branch of possibility, selected by a combination of physical law and environmental context. One of the most fascinating aspects of emergence is the appearance of purpose. Physical laws are blind, but emergent systems can display goal-directed behavior. A thermostat turns on when the temperature drops. A cell repairs its DNA. A neuron fires in response to a stimulus. These behaviors arise from patterns of information processing within the system. They are not fundamental properties of particles, but emergent functions. Understanding how purpose emerges from purposeless components is a central challenge in fields from biology to artificial intelligence. Quantum theory enters subtly here, as the basis for the chemistry and physics that enable life. Our narrative must also acknowledge the limits of our understanding. We have glimpsed the way entanglement shapes possibilities, how Bell's tests rule out hidden classical pictures, how information is physical and measurement is thermodynamic. We have explored decoherence and quantum Darwinism, the arrow of time, quantum thermodynamics, and macroscopic superpositions. Yet many questions remain. How does gravity fit into this picture? Does space-time emerge from entanglement? What is the role of consciousness in observation? Future parts of this documentary will delve into these mysteries, weaving them into our growing tapestry. For the moment, take comfort in the idea that the world you know is a pattern of patterns. You are not separate from the quantum substrate, but a complex arrangement of its possibilities. Each thought, each memory, each breath arises from atoms that once floated in ancient stars. The emergent reality you inhabit is both fragile and robust, delicate because it relies on coherence and redundancy, and enduring because its patterns are replicated across countless environmental fragments. The next steps of our journey will invite us to look deeper still, to see how the quantum universe continues to unfold its secrets. Like the gentle repetition of waves on a shore, we now linger over the ideas we have introduced, allowing them to sink in more deeply. Entanglement may seem like a simple correlation, but its roots run through the heart of quantum theory. When you prepare two particles in a shared state and then separate them, you are not just assigning values to each. You are creating a single spread-out entity whose identity is defined by relationships rather than intrinsic properties. Those relationships persist even as the components drift apart, like two violin strings tuned to resonate in sympathy across a room. To grasp the nuance of entanglement, consider the Einstein-Podolsky-Rosen paradox. Einstein and his colleagues believed that quantum mechanics must be incomplete because it allowed pairs of particles to have correlated outcomes without specifying real properties in advance. They proposed that hidden variables determine the outcomes, and that measuring one particle simply reveals what was already there. But as we have seen, the correlations predicted by quantum mechanics are stronger than any such hidden plan could produce. These experiments force us to accept that at a fundamental level, nature is not built from independent blocks, but from interwoven possibilities. Entanglement can be visualized as a shared wave function that cannot be factored into separate parts. For a pair of entangled qubits, the combined state might be something like 1 over square root of 2 times 0, 0 plus 1, 1. In this state, neither qubit has a definite value, but the pair is perfectly correlated. If one is found in the 0 state, the other will also be 0. If one is found in the 1 state, so will the other. The key is that there is no way to assign a pre-existing value to each qubit without breaking the entanglement. The connection arises because the state is built from sums of possibilities rather than fixed assignments. Experiments using photons provide vivid demonstrations of entanglement. Pairs of photons can be produced in crystals through a process called spontaneous parametric down conversion. A single, higher energy photon splits into two lower energy photons whose polarizations are entangled. If you measure one photon's polarization in a certain direction and find it vertical, the other will be found vertical if measured in the same basis. If measured in another basis, the outcomes will still be correlated in a way that depends on the relative angle. These experiments are routinely performed in undergraduate labs, making the once controversial idea of entanglement a practical tool for students. Beyond the lab, entanglement underlies emerging technologies such as quantum cryptography and quantum teleportation. In quantum cryptography, entangled pairs are used to establish shared random keys between distant parties. Any eavesdropping attempt disturbs the entanglement, revealing the intrusion. In teleportation, a quantum state is transferred from one location to another using a shared entangled pair and classical communication. The original state is destroyed at the sender and recreated at the receiver. Such protocols demonstrate that entanglement is not just an intellectual curiosity, but a resource for processing information in ways impossible classically. Einstein's discomfort with entanglement stemmed partly from its conflict with classical intuitions about locality. He imagined that physical influences must travel no faster than light. Entanglement seems to defy this by creating correlations across arbitrary distances. But careful analysis shows that no information travels faster than light because the outcomes are random. Only by comparing results after the fact can observers see the correlation. Thus, quantum theory preserves causality while revealing that the structure of reality is non-local. The philosophical implications of entanglement are profound. The universe appears less like a collection of separate objects and more like a web of relations. Properties that we attribute to individual systems depend on context and the way we choose to interact with them. When we separate entangled systems, we are slicing through the web, creating independent fragments. But the memory of the original unity persists in the correlations between outcomes. In this way, entanglement invites us to see the world as inherently holistic. The experiments inspired by Bell's theorem are among the most convincing pieces of evidence for quantum mechanics. In the 1980s, Alain Aspect and his colleagues performed tests using entangled photons and polarizers rotated independently at each station. Their results violated the Bell inequalities, showing that the correlations could not be explained by hidden variables. Later experiments closed various loopholes. Detectors were improved to ensure that most entangled pairs were counted, and measurement settings were changed rapidly to prevent any subluminal communication. In recent years, simultaneous tests using human random number generators and distant telescopes have further confirmed the quantum predictions. The consistency of these results across different platforms underscores the robustness of entanglement as a feature of the world. Understanding Bell's theorem requires appreciating the assumptions underlying classical realism. In a local hidden variable theory, the outcome at one detector depends only on properties carried by the particle and not on the measurement choice at the other detector. Bell's inequalities quantify the maximum correlation such a model can produce. Quantum mechanics predicts violations of this bound because the outcomes are not predetermined, and because measurement choices affect the correlations. The experiments show that nature obeys the quantum predictions, forcing us to relinquish the idea that particles carry pre-assigned answers to all possible questions. Instead, answers are created in the act of measurement. Hidden variables might still exist if we allow non-local influences, but such theories would need to violate relativity or incorporate conspiratorial mechanisms linking measurement choices. Most physicists accept the simpler conclusion. Quantum mechanics is complete and entanglement is real. This acceptance does not imply that we understand why the world is this way. Rather, we acknowledge that our classical intuitions are not a guide at the fundamental level. Future theories might unify quantum mechanics and gravity, shedding light on entanglement from another angle. For now, experiments leave little room for classical alternatives. Bits and qubits deserve deeper reflection because they embody different ways of representing reality. A classical bit is like a switch that can be on or off. Its state is definite and can be read without disturbance. You can copy bits freely. Duplication does not change them. By contrast, a qubit is like a spin pointing in some direction on a sphere called the Bloch sphere. The North Pole represents the zero state, the South Pole the one state, and any point on the surface corresponds to a superposition. Measuring the qubit along a certain axis tells you whether it is north or south of the equator relative to that axis. But this measurement disturbs the state. Superpositions can interfere, producing patterns that have no classical analogue. For example, if a qubit is in a state equal to 0 plus 1, measuring in the computational basis yields 0 or 1 with equal probability. But if you first rotate the basis and then measure, you can transform the state into one that yields a certain outcome. This ability to manipulate probability amplitudes is the source of quantum algorithms' power. By designing sequences of quantum gates that exploit interference, one can compute global properties of functions, factor large numbers, or search unsorted lists more efficiently than classical algorithms. The entanglement of many qubits creates a computational space that grows exponentially with the number of qubits. However, the exponential richness of quantum states comes with fragility. When a qubit interacts with its environment, coherence is lost, and the system behaves more like a classical bit. Building quantum computers therefore requires isolating qubits from noise while controlling them precisely. Different physical implementations exist: superconducting circuits, trapped ions, photons, spins in silicon, and even defects in diamond. Each platform has its own challenges and advantages. Error correction schemes allow us to encode logical qubits in entangled states of many physical qubits, detecting and correcting errors without measuring the quantum information directly. These techniques push the boundaries of our engineering and our understanding of quantum dynamics. Landauer's principle connects the abstract world of information to the concrete world of energy. The constant kBTLN 2 sets the minimal heat cost for erasing one bit of information at temperature T. At room temperature, this amount is tiny, but in large computers with billions of operations, it becomes significant. It is not the writing of information that costs energy, but the erasure, the act of resetting a memory register to a standard state. In reversible computing, computations can in principle be performed with arbitrarily little energy cost, provided you avoid erasing information. The cost arises when bits are discarded or overwritten. The link between information and thermodynamics also appears in the so-called second law of information theory. The entropy of a closed system never decreases on average. This law can be derived from the microscopic reversibility of physical laws combined with the coarse graining imposed by measurement. When we ignore correlations or throw away bits, we effectively increase the uncertainty about the system's state. Landauer's principle quantifies the energy cost of this lost information. In a world where information is physical, thermodynamic, and informational entropies become two sides of the same coin. Maxwell's demon highlights the subtlety of information and entropy. The demon gathers information about molecules in a gas, allowing only fast molecules to pass through a door in one direction and slow molecules in the other. It seems to create a temperature difference without doing work. But when we consider the demon's memory, we see that recording and erasing information balance the books. The energy spent erasing the demon's memory prevents a violation of the second law. Landauer's insight reveals that there is no free ride. Ordering the universe locally must be paid for by disordering it elsewhere. Decoherence is a mathematically tractable process. Suppose a quantum system is in a superposition of states, each with its own phase. When the system interacts with an environment, the phases associated with different components become entangled with environmental degrees of freedom. For an observer who does not keep track of the environment, the off-diagonal terms in the density matrix vanish. This means that interference between those components is suppressed. The diagonal terms remain, representing a classical mixture of outcomes. Decoherence transforms coherent superpositions into incoherent mixtures without the need for a mysterious wave function collapse. The timescale of decoherence depends on the strength of the interaction and the number of environmental degrees of freedom. For a macroscopic object interacting with the air, decoherence can occur in picoseconds or less. Even for a dust grain in interstellar space, cosmic microwave photons and stray particles will decohere position superpositions within microseconds. In contrast, for a well-isolated atom in a vacuum trap, decoherence can take seconds or longer. This wide range underscores that decoherence is ubiquitous, but can be controlled by careful isolation. In describing decoherence, we should emphasize that it does not pick out a unique outcome. The transition from quantum to classical is not about selecting one branch. It is about suppressing interference between branches. Each branch can be thought of as a potential classical history, and decoherence ensures that these histories no longer interact. The superposition remains in the global wave function, but from the perspective of any observer embedded in one branch, the other branches are effectively inaccessible. This picture resonates with the many worlds interpretation, but one need not commit to that view to appreciate the role of decoherence in producing classicality. Pointer states are the stable points in the storm of decoherence. They are defined by the property that the environment leaves them intact or only weakly perturbed. In other words, interactions with the environment simply imprint the pointer state onto the environment without scrambling it. The pointer states of a quantum system depend on the specific details of the interaction. For a harmonic oscillator coupled to an electromagnetic field, coherent states may act as pointer states. For a spin in a magnetic field, the aligned spin states are stable because photons scattering off them carry information about the spin orientation. Records, in this context, are durable imprints left in the environment. When a photon scatters off an object and travels to your eye, it carries information about the object's color, shape, and position. Millions of such photons converge, providing redundant evidence. These records form the basis of objectivity. Multiple observers can independently access different copies and arrive at the same conclusions. Records are not necessarily perfect. They can be noisy or incomplete, but when enough copies exist, the signal overwhelms the noise. This redundancy is what gives the classical world its solidity. Quantum Darwinism formalizes the idea that stable states proliferate. Borrowing the metaphor of natural selection, we can imagine that different quantum states compete for survival in the environment. Those that are easily recorded and robust under copying are like fit organisms. They reproduce their information widely. States that are fragile or hard to copy quickly die out, leaving little trace. Over time, the environment becomes populated with information about the survivors. This process does not involve any conscious selection. it is an automatic consequence of interactions and copying. In this view, the classical world is the outcome of a natural selection process, operating on quantum information. The arrow of time emerges from this interplay of copying and erasing. When information flows outward, correlations build up and entropy increases. When we erase information, we must dissipate heat. Our sense of past and future is tied to the availability of records and the irreversible cost of erasing them. The psychological arrow of time points in the direction of increasing knowledge about the world. We remember the past because there are records. We anticipate the future because those records and the laws of physics constrain what can happen next. Time, in this sense, is a narrative woven from correlations. Quantum thermodynamics studies how these principles operate in small systems where quantum effects cannot be ignored. Fluctuation theorems, like the Jarzynski equality and Crookes relation, quantify the distribution of work in non-equilibrium processes. These theorems show that while the average entropy production is positive, there are rare trajectories where entropy decreases. Experiments with trapped ions, superconducting qubits, and colloidal particles verify these relations, demonstrating that the second law holds statistically even when fluctuations are large. They reveal that work, heat, and information are intimately connected at the quantum scale. Macroscopic quantum phenomena remind us that quantum theory does not have a built-in scale limit. Superconductivity, superfluidity, and Bose-Einstein condensation are examples of coherent behaviors involving billions of particles. In these states, particles occupy a single quantum state, and their collective behavior cannot be understood by classical statistics alone. The resistance-free flow of electricity in a superconducting wire, or the frictionless flow of liquid helium, occurs because the particles are entangled and coherent. These macroscopic quantum effects challenge our intuition and inspire technologies like superconducting magnets, quantum sensors, and perhaps quantum computers. The resilience of macroscopic quantum states depends on protecting them from decoherence. In a superconducting circuit, the pair potential binds electrons into Cooper pairs that move coherently. Magnetic impurities or thermal vibrations can break pairs and destroy superconductivity. Similarly, in a Bose-Einstein condensate, interactions with residual thermal atoms can cause decoherence. Creating and maintaining such states requires cooling to near absolute zero, isolating the system from electromagnetic noise, and sometimes using active feedback. The experimental mastery of these techniques is a triumph of modern physics and engineering. Emergence as a pattern resonates beyond physics. In biology, evolution produces organisms that are more than the sum of their molecular parts. In ecology, ecosystems exhibit cycles and stability that cannot be inferred from the behavior of individual species. In neuroscience, consciousness emerges from neurons firing in complex patterns. In social systems, cultures and economies evolve rules and norms, patterns within patterns within patterns. The idea that simplicity gives rise to complexity through repeated interactions is a unifying theme across disciplines. Quantum emergence adds a layer. The raw material for all these patterns is itself a tapestry of possibilities. We can even see emergence in the arts. Music arises from vibrations in air, but melodies and harmonies are patterns in time that evoke emotions and meaning. Visual art uses colors and shapes to create patterns that our brains interpret as scenes, symbols, or abstractions. Literature weaves words into narratives that resonate with our experiences. The arts exploit our brain's pattern recognition capabilities, building emergent meanings from the arrangement of simpler elements. Perhaps the appreciation of beauty is our way of recognizing and celebrating emergent order. The interplay of determinism and randomness in quantum mechanics mirrors themes in human life. We live in a world governed by physical laws, yet our experiences are punctuated by chance. Our choices, shaped by patterns of experience and environment, can amplify small fluctuations into significant outcomes. Quantum theory suggests that chance is fundamental, not merely a lack of knowledge. In recognizing this, we may embrace the uncertainty of life as a space of possibility rather than a source of anxiety. The randomness at the heart of physics gives room for novelty, creativity, and free will. Feynman's path integral formulation of quantum mechanics portrays a particle's journey as a sum over all possible paths, each weighted by a phase factor. The classical path emerges because nearby paths interfere constructively while distant paths cancel out. Emergence arises again. The classical trajectory is a pattern formed by interference in the space of histories. This viewpoint unifies quantum theory and classical mechanics and invites us to view reality as a tapestry woven from countless possibilities. The patterns we observe are the result of constructive interference across the manifold of potential realities. In the quest for a quantum theory of gravity, emergence takes on a new dimension. Spacetime may not be fundamental, but emergent from more primitive quantum degrees of freedom. Approaches like loop quantum gravity and causal dynamical triangulations attempt to build space from discrete elements. The holographic principle suggests that the information content of a region is encoded on its boundary, hinting that the interior may be a redundant description. In the ADS/CFT correspondence, a gravitational theory in a volume is dual to a conformal field theory on its boundary. These ideas suggest that gravity and spacetime geometry may themselves be emergent patterns. Experiments testing the emergent nature of space are challenging but not impossible. Observations of black hole evaporation and the detection of gravitational waves provide glimpses into the interface between quantum mechanics and gravity. The information paradox of black holes, whether information is lost or preserved, touches on the interplay between quantum entanglement and the structure of spacetime. Recent developments propose that the entanglement structure of the boundary theory describes the geometry of the bulk. These concepts remain speculative, but offer a roadmap for the next frontiers of physics. As we approach the conclusion of this part, we reflect on the journey. We began with entanglement and the web of quantum connections that binds particles. We explored Bell's theorem and learned that no classical hidden variables can account for the observed correlations. We discovered that information is physical, that erasing a bit of information has a thermodynamic cost, and that bits and qubits represent different ways of encoding reality. We delved into decoherence and quantum Darwinism, seeing how the environment selects pointer states and spreads information across redundant records. We touched upon the arrow of time, quantum thermodynamics, and macroscopic superpositions. We considered emergence as a pattern, linking physics to biology, art, and consciousness. Our story does not end here. The next part will continue to weave these threads, exploring new landscapes where information, energy, and matter interplay in surprising ways. For now, rest with the thought that the classical reality you experience is not a given, but an emergent tapestry. It is a tapestry woven by countless interactions, a pattern that floats above the sea of quantum possibilities, gently rising from nothingness. The mystery continues, and we will journey onward together.